Perfect. I hope you can hear me now. There was an audio issue. I had my mic off. Right. What I was saying was, hello and welcome to this fourth episode of You and Type Check a Car. And if you're here on this side of the globe, good morning. It's a really pleasant morning out today. If you're from the West Coast specifically, even more because it's probably like 7 a.m. up there. But yeah, thanks a lot for joining wherever you are. So what I was saying is, I'm too excited about this part of the stream, this particular episode of the stream, because this project that I'm going to work on today, I've been planning to work on it for a while. Uh, uh, Not just on a stream, just like in general, I wanted to do it, and I just couldn't find a good excuse to do it. And now that I have this stream where I talk about compilers and I talk about low-level systems programming, optimizations, I think it fits. There are aspects of this project that fit well into what we do here. And yeah, I'm really excited to see how far we can push this project. Uh, so, if you have been following the announcements, today's episode is mainly going to be about me trying to build an emulator for the NES system or the Nintendo Entertainment System. That was a long time ago. If you have played games like Mario or Donkey Kong, like I showed in the video yesterday, those games were made for these entertainment systems. So, what we will be doing today is we'll be taking those ROMs and we would be will be emulating those to run on a modern PC like your Windows x86 or Linux x86 or whatever you're using. Uh, the there are various parts to this project, and we'll get into that soon. But I just want to like make a disclosure or like talk about this project a little bit. Is that I have done this before. I have written an emulator for this exact platform before, and that was a while ago. I think it was like 5 years ago or something. Let me actually share my screen and pull up that repository. Uh, my screen sharing not working. Interesting. Display capture off. Here we go. Yeah. So if you go to my GitHub, I have this repositories. Actually, it's pinned on my profile. So let's go there. Um, yeah, it's called EmuNES or emulator for the NES is how I had developed it. Um, This one is yeah, so last commit was like around some 6 years ago, which is when I was working on this for fun. The entirety of this is written in C. I don't think there's any C++ plus plus in it. Yeah, it's mostly C, some assembly, and some Python code for like drawing stuff for when I was like experimenting with it. But mostly it's like majority of it is just C and assembly. So the way this emulator was written was it basically is a translator. It's a JIT compiler in some way. So it accepts your ROM and it translates your instructions in the ROM basic block by basic block at a time, produces executable x86 code, and executes it on the fly. And as you jump to a different block, it sort of runs the whole cycle of compiling that basic block and executing those instructions. And if it sees that there is a new instruction, or if it reaches a new basic block it hasn't seen before, then in that case it sort of goes back, recompiles it, and does it. And if it has seen before, it just jumps to that existing block. And it keeps on doing this till you either kill the program or it reaches like a exit of some sort. Yeah, so this is how that worked. There's a comment. NES is exciting project playing with GBA libraries for a few months. Yeah, it's very simple. The CPU itself is pretty simple. But the fun part is actually a lot of the peripherals around the CPU. So this one has a CPU called the 6502, if I remember correctly. Yeah, 6502 microprocessor is what they used for running this NES. But it also comes with a lot of co-processors, mainly the PPU, which is the picture processing unit, and there's also audio processing unit, APU. I didn't implement the APU the last time I was doing this, mainly because the APU doesn't really actually change the execution. So the PPU actually is pretty tightly integrated with the CPU in that there is not just communication from the CPU to the PPU, like the CPU telling the PPU what to draw, but also the PPU giving back feedback in terms of some certain events happening, which meant that you need to emulate the PPU for the game to run correctly. And obviously, if you want to see something on your screen, you have to emulate the PPU. So that's the reason I implemented a PPU emulator along with it, but never bothered to do the APU. Maybe this time, if we have some time, I'll look into how the APU also works and we can implement that. Luckily, I have some resources about all of those things. And there's actually, if you go to OS Dev Wiki, I think they have a lot of resources about this too. But anyway, going back, what I was saying is it's a pretty simple CPU. Like if you look at the instruction set, there's just 256 instructions, pretty straightforward, nothing complex, which makes it pretty straightforward to like emulate and also maybe optimize it in some way. So yeah, it's a good target if you're trying to implement an emulator for the first time. I'm sure, are we starting over from scratch? Yeah, we are going to start over from scratch. We're not going to use any of the existing code base. In fact, the difference, what I was getting into the difference of what we did the last, what I did the last time and what I'm going to do this time. So like I said, the last time when I wrote this emulator, I wrote it so that it generates assembly on the fly. And the way it does that is what I had created is sort of this instruction database of handwritten assembly for sort of templates. These are basically templates for each of the instruction that exists on the CPU. So if you look at, say, let's look at ORA, which is like the OR instruction. It basically has this template where it moves a constant value into the RCX register, which is specifically mapped to one of the registers in the emulator, in the system. And then it does like a read ZPGX. We'll get into what this is. It's like some a macro that expands into a bunch of assembly instructions, does the OR and sets the not and the zero flag and so on. So I had written these templates by hand for each of the instruction on the hardware. And what the system does then is, as it runs and decodes the instruction, it picks up these templates. It sort of reads those templates from the compiled object file. And then it sort of patches those in at runtime, creates the code, and runs it. What this means is you have to basically write the assembly by hand, one thing. So if you target a different platform, so suppose you want to run this emulator on say ARM, you would have to rewrite this one specific file for translations to ARM. I did a good job of isolating the entirety of the rest of the system from this part, which means that you don't have to rewrite this thing for the whole system for everything. You just have to rewrite the translations for whatever your target is, and it would just work. Now, there's also this one assembly file which has some hard-coded sort of entry and exit blocks, so you have to rewrite that too, but that's about it. And then everything else is sort of like normal C. What we'll be doing this time instead is we'll be using BuildIt, one of my research projects, in fact, one of my main thesis project, to actually implement a compiler. And that's actually one of the biggest use cases of BuildIt. It is to create these small, tiny DSL compilers and get good performance out of them. So we'll try it. I have never done this before, by the way. Honestly, I have never tried to compile down any of these kind of instruction sets to C code or any of using BuildIt. So this is going to be an exercise for all of us. I'll probably be struggling with some things, but I think it'll be learning experience for all of us. So what I'm going to do is I'm just going to quickly show you how this old repo looks like. So we can just see what you have to implement. So if you, yeah, it basically, I've already compiled it. I think so. Yeah, I've already compiled it. So if you just run munus.out, I have two ROMs saved. So I have Super Mario Bros. And I have Donkey Kong saved. And then what I was talking about is the translation file. So you provide as an argument the translation database of the instructions, which has all the templates pre-compiled as the ELF file. And this is something what you get. So you get basically another thing I screwed up at the time was I kept the drawing very small. The PPU draws very small. We could change this. It should be a minor change. But anyway, so you can actually play the game. I think I've signed A to A space to B, and the arrow keys are basically, oh yeah, oh, of course I can't play. But anyway, so this is gonna be the goal for today. I hope you guys can see this. There's like a small screen here which shows the game being played, and just to show that this is not specifically for Super Mario Bros. Oh, sorry. We also have Donkey Kong as one of the other ROMs I had found on the internet at the time, and that works in the same way. So, yeah, it works same way. There is one specific thing which I had not implemented correctly. We will probably get to that eventually, and I'll explain what that meant for this one. I was sort of like hard coded in some way, which took care of how Mario works specifically. But in general, we will not do those kind of hacks this time. We'll do a proper implementation. Okay, so this is gonna be our goal for the end of this, like not today's stream, but this is gonna take a little bit longer than today. So we'll try to get how much ever we can today, and then later we'll add all the fancy stuff. Okay, so yeah, I've already made a repository for us to start with. Just have a git ignore there, and this is where we'll be starting from scratch. But before I get into start like implementation, I just wanna like draw a picture of how BuildIt comes into this whole picture. So let me share my iPad again. Give me a second. All right. Hmm. Okay, there we go. We have our screen now. Perfect. So what I'm gonna do now is explain how BuildIt fits into the whole picture because it's not entirely obvious. So what do we want to do? We want to write a sort of a compiler that takes in, let's call this the NES compiler, right? That takes in a ROM and emulates it. So what is essentially emulation here? Emulation is sort of a two-stage thing here where we first produce a executable or some sort of like x86 instructions, and then the inputs that are coming in from the controller, from the picture processing unit, and other stuff, you get the execution. So you get basically a frame where Mario is playing some jumping around the hoops. So yeah, this is the whole picture of what we want to do, right? But we can't like I don't want to do this in a traditional way where so this is the original traditional way was like we take the ROM, we produce some x86 instruction in the compiler, we produce the executable and we start running it. But let's see how BuildIt fits into this picture. So before I get back to this, let me just quickly talk about what BuildIt is to remind you. It's a multi-stage programming framework in C++. What that means is you can write code in stages. So the simplest way to explain this is suppose you have a program like this that suppose takes two inputs. Let's call it input A and input B, and returns say A plus B, right? This is the simplest function that you can write in C++. I have A and B integers and returns A plus B. Now let's call this function foo. Uh, what BuildIt lets you do is split this execution in two stages. So what you can do is I'm gonna say, hey, I know this function foo takes in two arguments, but I'm only gonna provide you one argument for now. I'm only gonna provide you int a. What this ends up doing now is actually producing another function. Let's call it foo dash, which now accepts the remaining input. So it accepts b here and produces a plus b. So for example, if I provided a as say 5, the code here that it produces would look something like int foo underscore 1, int b, because now it accepts b, and returns b plus 5. Whereas our original code was simply foo int a comma int b, return b plus a. Suppose it was like this is what it will produce. It will basically evaluate the code entirely for what a was, and produce a specialized code for that specific input. And it will take all the remaining inputs in the next stage. And this it does through sort of like a lot of low-level tricks in C++ and operator overloading and a bunch of things that you can read about in the paper, or I can also cover it at some point. In the past, we have fixed some bugs in BuildIt, and at that point, we sort of covered some of the details of how the internals work. But the point is, it lets you write code in stages, and that's the key point. Okay, so how do we use this to write an emulator? Let's think about what an emulator's picture looks like actually. Without, oops, sorry, I deleted my pen. Yeah, let's think about how a emulator picture look like. So if you write a general purpose sort of an interpreter for NES, right, which basically line by line takes an instruction and sort of simulates the behavior by updating local variables, or basically changing the state of the program. That's the easiest and the most sort of general implementation you can write for a system like this. So you can just like you must have heard of, like, say, Python interpreter, or like interpreter for languages, where you just line by line interpret what the behavior of the instruction is. Suppose you write an NES interpreter like that. What are the inputs to this interpreter? There are two inputs. One is the code, or the ROM. So the instructions in the processor that you want to sort of simulate, and you take all the inputs. So your controller inputs, your PPO inputs, everything is coming in at the same time, and then this produces the behavior that we want. So Mario playing and jumping over the pipes. This is the whole sort of like a standard emulator, how it would work. Now suppose we write this system using BuildIt. So we write this on top of BuildIt. What do we and say we provide this input, the ROM code, as the first stage input, which we will call, for the entirety of this discussion, static input, and let's call this the dynamic input because it comes at the runtime. So what will happen in this case? BuildIt would take this interpreter and produce only take one input now, which is the ROM code, and produce, let's call this NES interpreter still, and it will produce another piece of code which is sort of specialized for this ROM, right? This is specializing for this ROM, and now this will take the remaining inputs like the controller and the PPU, and this will give us the game. So if you let's call this, like, say, code gen, right? Generated code or whatever. Now, if you look at this whole process, this diagram that I have drawn, the PPU input and everything also comes in at this time. If you look at this picture, and if you scroll back and look at this picture, they're exactly the same. What we have essentially written modulo labels, it's exactly the same. We have a first box which accepts the ROM and produces some code which then actually runs with the controller inputs and the PPU inputs to run the game. And this is exactly what it looks like. The details are that this is done through a multi-stage programming framework. So this basically comes down to one sort of statement, which is staging or multi-stage execution of an interpreter is a compiler, right? So we took an interpreter, wrote it using a multi-stage programming framework, and when we ran it, it actually produced the code for that input, which is basically what a compiler does. This is not new. This insight is not new. In fact, this was given a long time ago. It's called the Futa-Mirror projections. There are actually three of them, three such theorems similarly, and we'll be using the first Futa-Mirror projection today to write a compiler for these NES ROMs. And why do we want to use this technique? The simplest idea is to actually reuse a lot of infrastructure. So the last time when we did this, I wrote all the instructions by hand, explained to the CPU what needs to be done exactly when a particular instruction is seen and so on, and I tried to optimize it along the way as I did it. But if we take this approach and we generate some C code out of those ROMs, we can actually reuse a lot of existing infrastructure. we can basically call an existing C compiler, an optimizing C compiler like GCC or Clang, for your specific target, like say ARM or x86 or I don't know, RISC-V, whatever, and they will just work because what you're producing is generic portable C, which should run on every platform. The side effect of this is also that you have just now created an executable which doesn't need a ROM, right? Like the previous interpreter still needed the ROM all the time because you had to implement those instructions, interpret or like sort of emulate those instructions on the fly. But now we can also make it in a clear sort of distinction. You can say, okay, here's a ROM, give me C code corresponding to it, and that's the entirety of your Mario code. That would be nice to have, right? So basically translating the whole ROM into C, and then you can compile it however way you want. We'll get there eventually, but we'll start slow, and we'll see what it takes to emulate this whole system. There's a message in the chat. Game Boy Advance uses ARM v4 and ARM v5. NES using 6502 ISA is a new information. Yeah, NES is a very old system. Let's actually check when it came out. I am not sure how old NES is. NES release date. Yeah, it came out in 1985. I don't think we had ARM v4 or ARM v5 at that time. But yeah, it's a really old system with a really old processor. The modern ones are really powerful. Like I know Game Boys have like a lot of memory now and bigger processors and registers. This one is such a like old system that it only has 64 kilobytes of memory. So your addressable memory is just 2 bytes, two bytes of addresses for the memory. It's a 8-bit processor, which means all your sort of instructions are also 8-bit. It's very simple but really powerful. Where the power actually came for all these NES systems and the SNES and everything that came later was the developers working on this platform. They were really smart. Like they basically got the best out of the hardware. If you try to understand all the assembly that they wrote, by the way, they wrote assembly. They did not have access to higher level programming languages like we do. I mean, they had access to some of them, but I don't know how much they used that for compiling down to the NES. But that assembly is very hand tuned and optimized. We'll look at all the tricks and stuff they did to make things work, and it was beautiful. So I mean, yeah, the first time I like 6 years ago when I was looking at all these things, it was mind blowing to me. So, but yeah, we'll get to that later. Let's just get directly into what the system looks like. The whole sort of. Oh, I was not showing you the date. Yeah, oops. Yeah, it came out in 1985. That's what I was trying to show you. Yeah. So yeah, without further ado, let's just look at the whole sort of architecture of how the system looks like, and then we will start by implementing a sort of compiler for the CPU, which is the 6502. And then we'll start moving towards the other harder aspects like the PPU and so on. I at least expect to finish the CPU today to a extent where we can run some basic programs. We'll not be loading ROMs right now. That actually is yet another sort of massive piece of thing because the ROM format is in a very specific way. So you have to sort of like decode that format, identify headers and stuff out of that. So we will do that. But maybe we'll start with emulating the CPU, which is the most sort of interesting part to me, at least for now. So yeah, let's get back into it. I'm gonna stop my window capture and stop sharing my Zoom. Okay. If you have any questions, please drop them in the chat. I will try to look at them as I go. All right. Okay, so the first thing I'm gonna do is I'm gonna just create a basic directory structure that I like. So I always like to have a source directory and I always like to have an include directory. My build directory is usually made by the makefile, so that's what we will do now. Uh, I am also gonna do this trick, which I will explain later. Oops, sorry. I'll explain what that line specifically does, but let's hold on to that for now. So the first thing I usually like to do is to get the base directory, which is basically where the current repository is located, and an easy way to do that is by using the shell pwd command. So this just tells you where you are currently. And then everything else will be relative to this directory. So I'm going to say our build directory is going to be sorry, base directory slash build, and this is going to be my default build directory. If I wish, I can change this. I'm going to use a question mark equals. Then I'm going to get my source directory, which is always going to be base directory slash source, my include directory so that I can have all my headers and everything uh, referenced in one place. And that's about it. Now I am just going to make sure that the build directory exists. This is, I'm using GNU Make, which is what I like to use. So we will just say mkdir-p build dir. The good thing about GNU Make is you can have statements at the level of the sort of scope of the file which get executed before the make file make target start running. And this is very helpful. Sometimes you can do cleanup, you can create directories like this. Um, and there we okay, so it doesn't have a target. Let's make a target called all, which is basically just executables. So yeah, all our things should be executable. This is a phony target. I'm just gonna add it, but in general you don't have to because no, please use other tools to prolong the stream. No, I'm not gonna use other tools. I'm gonna write my own make streams, make files like I always do. Uh, yeah, for executables, I'm not going to say anything for now. And there we go. Our build directory is created. It has nothing inside it, which is good. And here's what I'm going to do. I like to do it this way so that I can just, I like to do sort of an out of source build. I always get a separate build directory. That way I can, clean should just be my clean can just be delete the whole build directory, and that way I don't have to think about it at all. Okay, so let's start with executables. We have just one executable, which is going to be our emulator. So let's call it build dir called NES underscore compiler. This is actually technically a compiler. Uh, so executables different on executables. Great. Uh, Now I need the object file. So I'm just gonna, there are usually better ways to do this using like wildcards and stuff like that. I'm not gonna do that. I'm just gonna like manually list out the OBJs that we're going to compile. So I'm gonna say build dir, because it's a small project. This won't have too many files. So I'm just gonna manually write it. So let's write a simple driver.o, which is what it will be using. So then I'm gonna say my build dir call slash NES compiler depends on OBJs, all the object files. Uh, and how are we going to compile the thing? We're gonna call CX. It's gonna be it's gonna be a C++ project, not a C project. So CXX dash O dollar at, which is the target, and then we're going to compile all the right hand side ones. So that is dollar. That takes all the dependencies and links them together into the target. So this should produce all the object files, but we also have to tell it how to build those object files. So that's going to come from let's say we have a specific .o that we need, then that should come from the source directory slash that specific .cpp. But this also depends on all the includes. So what I'm going to do is I'm going to get all the includes first, which is going to be includes wildcard um, include dir star dot h. I can also concatenate like subdirectories, but I think I'm going to keep all my headers in one directory, so this should be fine. And then I'm going to say it depends on all includes. But this time we don't use the caret sign because that will also try to compile the header files, which we don't want. So I'm just going to say cxx dash o dollar at, and then I'm just going to use dollar less than. But what I'm also going to do here is I'm going to put this flag called C flags so we can set our C flags separately. And the way I like to set my C flags is I like to have O3 obviously. and then I like to have W error and W pedantic so that I'm keeping track of what I'm doing. But uh, I'm also going to need to add build it as a dependency, which is what we'll do next. But before we do that, let's just also do LD flags for the linker. For now, it's just going to be empty, but let's keep it still defined. And then we have the LD flags added to the linker. Okay, this should, okay, so it says there is no target to make driver.o, which is good because driver.o requires a corresponding CPP, which it doesn't have. This is in the right order, yeah. So what I'm going to do is now I'm just going to say source driver.cpp. Let's make a simple uh, hello world file. Actually, not even a hello, just an empty main should be good. And there we go. We got a linker error which says cannot use executable file. Oh, of course, because I forgot to put the dash C flag on the compilation. Here we go. Yeah, this should do it. And but that needs to be cleaned up first because we miscompiled. And perfect, we have our NES compiler running. So all the oh, I should probably bump up the font. Sorry about that. Yeah, so you guys can see this better now. We have our gonna show you my make file again. A simple make file, nothing fancy about it. Just uh, uh, identifies where all the files are using the base shell pwd, and then just creates all the other paths, sets some variables, and compiles the executable. Next up, what we're going to do is actually add BuildIt as a dependency. So we'll start by cloning BuildIt, or let's clone it from, yeah. So you go to the repository. You usually take the HTTPS one because you don't want to, if you want to share this with others. So then you say git submodule add BuildIt. So now it has added BuildIt as one of the submodules inside this repository. What we're going to do is without building, not as part of our build system, I'm just going to make BuildIt first so that all the headers and all the generated headers and all the object files and library files are in place. You can also change your build system to actually build your dependencies, which I do for like bigger projects where I know that the depending library might also change from time to time. Uh, but here I know that I'm going to use a fixed version of BuildIt. I'm not going to change it. So I'm just going to build it upfront and then add it. So the official way of sort of like supporting reading sort of the flags from BuildIt or compiling against BuildIt is actually documented on this documentation page. This page is not complete, it's still work under progress, but if you look at it, this is using BuildIt in your project has this sort of specific way of doing it, which is to get the compile flags and the linker flags to link against BuildIt and to compile with BuildIt by using its build system. This is like a sort of a drop-in replacement I have created for package config basically. And this is useful because BuildIt sort of needs you to use different flags based on what configuration BuildIt is compiled in. So suppose BuildIt is compiled with debug, or if BuildIt is compiled with the special feature we have called recover variable names, you need to use different flags and you need to use sort of different linker flags in your code. Basically, BuildIt also has some dependencies which are only required under certain configuration, but for the user to not have to worry about all that, we just ask them to use sort of this path. So that's what I'm gonna do. I'm gonna just copy this from here. Let's go back to our code. Uh, I'm gonna make a new variable now called builditdir because this also I'm gonna do question mark equals. So if the user wants to use a different version, they can specify this as part of the configuration. So then this goes default is goes to build it. And now I'm gonna say, actually I'm just gonna add this here. So this just directly goes here. Path to build it repo is build it dir compile flags. LD flags are exactly the same. So they just, instead of taking compile flags, you take linker flags. And this changes to And there we go. So now we have built it and its dependencies and everything. It creates linked and sort of used in our build path. So I'm just going to say make clean. Uh, Nothing happened. That is interesting. I think it's not able to find the correct path. Yeah, is. Oh, it needs the build path. No, no, it doesn't need the build path. Path to the build repo. You know what? Let's just do this. Make C build it. I'm assuming this is right. Yeah. Um, Compiler flags. Compile flags, not sorry, compiler. Oh, okay. So it does print those flags, which is great. Um, oh yeah. So this is a shell, so it's not just a variable. Yeah. So you need to use shell here. That example was from the terminals. That's different. But yeah, there we go. Now we have our headers being like the header locations being pulled it from where BuildIt is built. The linker flags for BuildIt, including like whatever other dependencies it has, where those headers are. It's all just put in correctly. Okay, so we have a basic sort of working skeleton of our code. Let's start with like getting into what we need to implement yeah, the 6502 CPU emulator. So I'm going to start by making this materials directory, and I'm just going to keep all the materials that we use for this one here. I'm just going to copy actually the manual for that processor, which I found a while ago. Where is it? Oh, let's see. So we have 6502. I'm going to copy it into materials. Yeah, let's see what that 650216. So this is basically a description of the processor, the whole processor, including like the registers, the addressing modes, the instructions, everything. So if you scroll through this, it has basically details of all the operations and how they are emulated and so on. The good thing about this is these instructions, even if there are like 256 of them, they are sort of combinations of instructions and different addressing modes. So once we implement all the addressing modes and once we abstractly implement sort of all the logical operations, getting all those instructions will be very simple. Like there's a few basic type of instructions, and then there is the instructions, the addressing modes, and once you sort of combine them, we get all the instructions. So hopefully it won't take too long for us to implement this. But the basic thing is we need to implement the sort of the hardware features that the instructions have access to, which is like the register, the memory, and so on. So yeah, there are a few registers in 6502. You have the accumulator, which is probably the most important register if you know from like any other assembly that you have used before. Accumulator is sort of the primary register for sort of all operations you would end up doing. Like if you're doing additions or if you're doing or bitwise and whatever, you will be using the accumulator register to compute the results. The X index register and the Y index registers are sort of memory registers in that they let you index into like the memory for like doing indirect loads and stuff like that. We will see how they are different and what they exactly do. There's a status register which basically has like flags. So like just like x86 has your zero flag and your carry flag and so on. They similarly have the carry flags and zero flags and interrupt flags, decimal mode status flag and so on. We'll be implementing all of these, don't worry about this. Then there's the actual program counter, which is basically the PC where you are currently in the execution. This one we will not have in our generated code because our generated code will not have a PC. It will basically just be a straight line C code or with some like control flow and so on, which will implement the program. So we won't be generating the program counter. We will be generating the stack pointer though, because we have to emulate going up and down the stack. It would have been nice if we had like completely encapsulated like functions in NES as functions in C++, so that way we don't have to even have the stack pointer, but that's not exactly how it works. There are instructions which sort of address stuff relative to the stack, pointer and stuff, and that doesn't exactly match with what the C++ compile code would look like. So, or C compile code would look like. So we will be emulating the stack pointer completely. And there we go. The next thing is the addressing mode. So the basic gist is instruction needs operation to work on, and there are various ways of encoding in the instruction how to sort of obtain those operands. Um, so even though it's called addressing mode, it's actually all types of inputs. It's not just things that come from the memory. So you have things like immediate, which is basically saying the value that you're going to compute on is stored as part of this instruction. So in this mode, the operand's value is given in the instruction itself. In assembly language, this is indicated by hash. So there is a corresponding assembly for this, by the way, which actually the last time I implemented, I also wrote a printer for this. So we can sort of like debug and see what the instructions are while we sort of write this. I might just copy over that sort of table of the printer from the previous code. But yeah, if your operand has a hash or pound sign before the actual value, then that means it's an immediate value. So when it says LDA pound $0A, this means load the accumulator with the hex value 0A. So this is hex because all the assembly is just in hex. Hash here, actually, wait, maybe the dollar sign means hex here. I'm not sure, but yeah, we'll get back to that. And the pound sign here says that load the value exactly. There's no memory access here. So in machine code, different modes are indicated by using different codes. So LDA will be translated to different codes depending on the addressing mode. So this is great. This means that we don't have to sort of break down instructions and identify parts of the bits and stuff to see which addressing mode it is. They're just straight up different bytes they map to. Like this instruction has basically 4 or 5 versions. All of them have different byte values which just correspond to those instructions. So yeah, that's the first addressing mode, which is load an absolute value from the instruction itself. Then you have the absolute and zero page absolute, which is what you would think of like memory addresses. So when you have LDA 3F56, this 3156, this basically means go and load the value that's stored at 3156. So yeah, that's the absolute addressing mode. There's a special sort of zero page in the 6502, which is uh, made so that you can access it fast, or you can access it with fewer sort of shorter instructions basically. So if the address is on the zero page, that is the address. The pages here are 256 bytes, by the way. So 1 byte addressable pages. Any address where the high byte is 00, that's the first page, right? If your first page has addresses from range 00 to FF, then in that case, only 1 byte is needed. The processor automatically fills the high byte with 0. So this has an addressing mode, like this is called the zero page addressing mode. Again, this is a separate instruction. The byte encoding for this is very different. That way we won't have to confuse ourselves with like, what does that instruction mean? So in this case, you only provide the higher, the lower, sorry, 8 bits. You don't have to provide the higher bits. And yeah, uh, right. So the zero page absolutely is usually just called zero page. Zero page absolute is just called zero page. We will make one of those addressing modes. Then we have the implied addressing mode. This is basically a no op addressing mode, or it basically says there is no addressing mode. This has like there is no operand, basically no operand addresses are required, they're implied by the instruction. So for example, transfer accumulator contains to X register. So here it's it doesn't require an operand in the instruction, but it still has sort of like it could have load or store. So what this is saying is transfer accumulator contents to the X register. Like just move the accumulator to the X. That's what it is. The yeah. So that way yes, there is a destination, there is an addressing mode, just like register addressing mode, but it's just different instructions. Like TAX is specifically for that. Then you have TAY, which is transfer to accumulator to Y, and that would be a separate instruction. You could think of it as the TA instruction with X and Y as operands, but that's not what they do. This is completely separate. And then you have the accumulator addressing mode, where in this operation, instruction operates on data in the accumulator. So again, no operands in the instructions are required. You just have LSR, which is logical bit shift right. and so on and so forth. Indexed and zero page index. These are the ones where we do sort of more complicated memory accesses. So in this mode, the address is given by is added to the value in either the X or the Y index registers to give the actual address of the operand. So this is more of like I have a base address and I have the X and Y registers, which are sort of like telling me how far or what's the offset into where this address I'm loading or storing or whatever I'm performing from is at. So we have like say LDA 31F6Y. This says take take 31F6, add Y to it, and load the value from that into the accumulator. So yeah, it's the same. And then you can also combine this with zero page. So you have LDA 20X, which says add 0020 plus X. So yeah, it's pretty straightforward that way. And then you have the indirect one, which is basically only used for specific instructions, like say the jump, and there are a few other ones. Sorry, this one only applies to the jump instruction. Perfect. It's basically saying you have an indirect jump. So I have an address where your jump address is stored. So normally you could have a jump at say $215F, where it would just jump to $215F. By putting a parenthesis around it says load the address from 215F and then jump there. That's basically what this says. Yeah. This instruction takes the value of the bytes 215F and 2160 because all the values are 2 bytes here. So they're loading 2 bytes and uses that as the address to jump. So 3076 if that was stored at the location. Remember that addresses are stored with the low byte first, which means it is very much like our x86 system. So that's good for us. But again, we won't be relying on this. We will be sort of emulating this behavior completely. Okay. Then there's the pre-index register, which is in this mode, zero page address is added to the content of the X register to give the address of the byte holding the address of the operand. So this is more of like an indirect access where you're saying I have an address, add X to it or Y to it. Actually, it's only X. Yeah, add X to it, and then that's where the address is where I wanted to load the value from. So it's like a sort of like yeah, an indirect access basically, but not for jump, but for loading data, and it looks exactly the same. Yeah. So yeah, so this instruction is executed by adding 3e to 05 because the X register is 05. X register is 05. 3e was the base address we provided, so it adds 3e to 05, gets 43, then loads the address at 43 and 44, which is 2415, and then finally gets the value from there into the accumulator. So this is like an indirect load basically. You can also use it for stores and stuff like that. Yeah, and there's some like sort of caveats about how it works. Then there's the post-indexed indirect. In this mode, the content of the zero page address in the following gives the indirect address which is added to the contents of the Y register to yield the actual address. This is different. This is post-index. So you first load the value at the specific address provided. So you load the value at 4C, which is the zero page address. In that loaded value, then you add Y, and that gives you the final value to load from. So it's like the just the add is outside the parentheses basically. And yeah, the rest of it is same like before. And finally, you have the relative one, which is basically for jumps mostly, which is saying jump back or forward these many bytes. It's a single byte value, so you can't jump too far. If you have to jump too far, you have to use like one of the jump instructions with not the relative mode. You have to use like the absolute mode. Actually, not the absolute mode. You have to use the basic addressing ones. And yeah, that's your last instruction addressing mode. We'll implement these one by one. So okay, and then there are the actual set of instructions listed down in alphabetical order. That's it. That's all we have. These are the only type of instructions we have. So ADC is add memory to the accumulator with carry. AND is AND the memory with accumulator, and so on. There's the B as all the branch instructions. So like branch on carry, branch on carry clear, carry set, branch on result zeros. That's basically testing your flags and moving around. Then you have the clear flags and the set flags for all your for your flags basically. Then you have the comparison ones, compare memory and accumulator, compare memory and index X, compare memory and index Y, and so on and so forth. And then you have the decrement, increment ones, and then finally the jump ones. And that's your whole instruction set. But this combined with your addressing mode gives you all the 256 instructions that this hardware supports, this CPU 6502 supports. Actually, not all of them. Oh, there's a few more. Yeah, sorry, there's a few more left here. But yeah, what I was saying is not all 256 are implemented. There's a few sort of like blanks in the middle, which are like for future extensions or just like not valid instructions. But yeah, that's fine. There's nothing. Special about those. Okay, so this sort of the rest of the section just talks about detailed implementation of how each of those instructions are encoded and what sort of addressing mode they use and how it behaves. So this is like a small they have like a pseudo language of explaining what this produces, the behavior of this. But most importantly, it also has the number of bytes for this instruction, that's the encoding, and it also has the number of cycles it takes to execute this instruction. And this is important because we have to sort of emulate this behavior exactly at the level of the cycles. Because if there are a lot of sort of co-processors running inside the NES system, and they sort of run lockstep with the 6502 processor. If we don't emulate the number of cycles correctly, eventually they will start drifting, and you will basically have your picture drawing going in the wrong way and your CPU doing the wrong things, and you will just have bad implementation. So the number of cycles is very important. And yeah, there's a description for the for all of them. We'll implement them one by one, and we'll go ahead. Okay, so what did we decide today? We decided to write an interpreter for all these instructions, but written on top of BuildIt, so that everything it does gets generated as code rather than having to like execute it. It doesn't execute it; it produces the code. That's what we're gonna do now. I'm gonna start with some header files so we can put the description of our instructions and things into there. So let's say include instructions.h. So what I'm going to do this time is I'm just going to copy over the descriptions I wrote the last time, because they are just like literally byte encodings of all the instructions. So yeah, NES decoder, it just has like a bunch of enumerations for the different addressing mode, just different values of the sizes. So it tells you what addressing mode is of what size, and then just the names of all the addressing mode and the actual instructions. And there's also like a table which has the actual instructions stored there. What I'm going to do is I'm going to just like reuse some of this infrastructure so we don't have to write it again and again. At least the enums and the files. So I might change the names of these stuff because this was written a long time ago. So yeah, let's okay. Always put header guards close. Okay, this time we're gonna put it inside namespace NES, and within that I'm gonna say namespace instructions, or maybe instructions is too long. Uh, Instruction. So inside that, oh, we're gonna copy over some of these things. Yeah, so we have an enum which tells us what addressing mode we are in. So enum to identify instruction addressing mode. Let's give this proper names. Say addressing mode T. And these are the sizes. So they are just referencing the addressing modes. That's good. Addressing mode sizes should be fine. And then we have the actual names. So static const char, this all looks great to me. So for each addressing mode, we have basically written down what the name is. And it's just easier to print it that way. Okay, let's go to, yeah, so we don't need anything else from this decoder. There's an actual sort of instruction file which has all the instructions defined. We will obviously pick that up. But I don't need this struct which has all the information, or do I? Maybe it just makes sense to uh, store all that in the same format. Yeah, let's take this to. And this is a struct for like sort of defining our instructions, like all the information about our instruction. NES instruction T, and then we have a name and base cycles. Yeah, the base cycles is so that we know how many cycles uh, that instruction takes. There's also if you look at this, there's some if you look at the description of the cycles, there is a few star marks here. The star marks basically says it's a variable latency instruction. So add one if the branch occurs on this. So for example, we have the branch on C or branch on carry BCS instruction, which says jump to this address if the carry flag is set. But the latency of this is dependent on how far we are jumping. So if you're jumping on the same page, then it's 2 cycles. Sorry, it's 3 cycles, or it's 4 if we're jumping to the next page. It's yeah. So we'll have to take care of all this while emulating everything we are doing. So yeah, it's oh, this is the wrong file. Okay. So we have the addressing mode and we have the base cycles and the instruction file. So let's also look at the table. So this was NES instructions.c. Yeah, it's just one table which just has all the instructions and their names. So it has the names, it has the addressing mode, and uh, uh, um, the base cycles for it. There is a few nulls here, which basically says that this it doesn't have a valid instruction. Some of these instructions are not valid. Okay, so what I'm gonna do is I'm gonna copy this down first. I'm gonna change this a little bit actually. I don't like the way this is written. Uh, yeah. And the good thing what I've done there is the instructions are stored in the byte order. So instruction whose encoding is 00 is the first instruction. The instruction whose encoding is 01 or like 1 in the byte is the second instruction. That way, like once we load a byte to identify what instruction it is, we just need to index into this array and get what the instruction is. That makes things easier. What I'm also going to do now is instead of do we want separate enums for all of these, or should we just like do it based on strings? We could just like do string comparisons from this name to identify what instruction it is. I didn't need this before because I had manually sort of translated all those instructions. This was only for printing and for the base cycles. But what I'm thinking is I could just replace these with also enums to identify what instruction it is. Uh, but honestly, we could just use the strings. We could just say, like in our interpreter, we could just look at the string value and say, okay, what instruction is it? Uh, I think that should be fine. I don't think we need very complex instructions for that. Although, what I would have been nice is if I had kept the indices here. Hmm. So I can look things up quickly. Is there a way to add that? I just want comments to say what line number it is. Um, Annoying. I mean, we have our line numbers in the file to tell us where it is, but at some point later I'll add comments to say which instruction byte it is. Okay, so we have all our instructions. I should make this static because I'm putting it inside the header file, um, and I should change the type. Yeah, so this is gonna be. I was using the all caps convention at that time because yeah. Okay, so this looks fine to me. We're not using enum classes, right? We're just using enum, right? So we don't have to use the name everywhere. This looks good. So we have all our instructions encoded now. We should just make the static style. Great. Um, that's good. Now we can start writing the emulator. We have all the information about the instructions we have to execute, and we can start writing the emulator. So I'm going to close this. I'm going to keep this open. And we had the driver.cpp before. Now I'm going to have the emulator.cpp or the emulator header first. So let's do include emulator.h. This obviously needs a header guard. And this goes again inside namespace NES. I'm not gonna put this inside a separate namespace because that specifically was about instructions and I don't want like these name conflicts to like leak out of it, so I put them inside a namespace, but emulator is just gonna be inside NES namespace. Okay, great. So what do we need for this? We first of all need to include all BuildIt headers. So we're gonna say include builder denvar.h, which is our type for our second stage variables. And I'm also going to need builder static var dot h. Right. What I'm going to do first is I'm actually going to make some a type that sort of captures the context of what we need for the emulation. So like there's a few the registers, the start of the memory address, and so on and so forth. We need to sort of capture it into a struct so we can pass that around for all the operations. So I'm going to make struct NES context E, which is where we will have all our like context variables. By the way, before we do that, we need to have some data types for all our emulation. So I'm going to say type def n let's say NES word. Yeah, NES word. It's going to be an unsigned short because everything is a short. Uh, the benefit of this is now uh, you don't have to write long unsigned short and dynamic of unsigned short everywhere. You can just have normal type, small type defs. I'm also going to make a dynamic version of this, so that way we again don't have to do. Actually, you know what? Let's just use NES word. It's going to be DNES word. So this is going to say that this needs to be executed in the second stage, not in the first stage. And then we're going to, addresses are also words, so that's fine. But I'm going to need bytes too. So I'm going to say byte is unsigned char, NES byte. And then type def, then var of NES byte is DNES byte. Right? And I forgot to add builder here. That's in the namespace. Great. Now inside our struct, we're going to store some references. So let's make the registers first. That's the easiest to do. But what I'm going to do is I'm not going to actually store the registers in the context, because if we do that and we pass the context around, it just assigns those variables everywhere. What I'm instead going to do is I'm going to store references to these. The benefit of this is now I can create the registers once and pass around references to all these these variables. So I'm going to say DNES. Okay, what is the size of the accumulator? I think the accumulator is a byte. Mm, LDA, disks to Y. Let's look at one of those examples because they showed. Yeah, so the accumulator is a single byte. Loading contents of 2415, that is 6E into the accumulator. The accumulator is a single byte. Uh, so this is going to be DNES byte. But instead of just being a thing, we're going to make it a reference to an actual DNES byte. So that's going to be ACC, right? Our accumulator is the register. And then we have the, what registers are next? Accumulator, X index, Y index, and status registers. So that's, yeah, this is going to be a word because this stores uh, uh, this stores the whole address, not like the accumulator. And then we have the carry bits. Uh, the carry bits are also a single byte, but instead of storing it as single byte, what I'm going to do is I'm just going to store individual bits as separate values. That will make it easier for us to just access them. And there's no reason that these flags should be stored as a byte. There are a few instructions that actually store and load these entire status registers into memory, but we can sort of serialize it and deserialize it at that point. We don't have to make them into separate variables. So what I'm going to do is I'm going to make a separate like a carry flag value, which is just going to be a byte again. So I'm going to say DNES byte carry, right? What other do we have? We have 0, and then we have interrupt DNES byte 0, actually carry underscore flag, 0 underscore flag, and these should be references to interrupt decimal. This is set when a software interrupt is executed. So we have the break. Bit 5 is not used, so we don't have to implement it. We don't have to have it in our context. Then we have the overflow and the sign. So technically, we could have made this into a bool, but it's fine even if you do it as a char. I can change it later to be uh, it can be a bool if we need. So it's easy for comparisons and stuff like that. But I think it's fine. It doesn't really matter. And then we have what was it? Sign. Great. So we have the context captured, the context registers captured first of all, and then we're also going to capture as a first state variable, where does the address range begin? So this is something easy. We don't have to actually, uh, 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 this is just going to be like a static value. It doesn't have to be emulated. So this is going to be uh, DNES. Actually, we need two things for this. We need this is just going to be an absolute address where the values are stored. So we can just say char star main memory, right? This is where just going to be like a base address where all the values are stored, and the size of this is going to be always 0xFF because that's the maximum amount of addressable memory you have anyway. And all the addresses are going to be indices into the main memory. So whenever we sort of initialize the execution, we will tell the system where the main memory is. Right. We also need, but the other difference is we also need um, uh, the main memory at compile time and also the main memory at runtime. We need a reference to where the memory is when the program is running. So that is going to be stored as let's see, filter. Yeah, I should make a type def for this to just be easier. Type def filter char star DNES byte adder. This is just saying it's an address to a byte. Yeah. Uh, we're also going to need this. So DNES byte adder D main. Right. So this way we have a dynamic main memory, which is the memory state of the memory at the runtime, and then we have the memory at the compile time. This is so that we can look at the instructions, and this is so that we can use the memory as like execution. And that's about it. That's what we need to put in the context. As we go further, we will add more things to it, but for now, this should be good enough. Okay, we probably need a constructor for this, otherwise the things would complain. So yeah, NES context D. This is unfortunate. NES byte. Now I have to initialize all of them. I could have done this better, I think, but it's fine. I This is a one-time thing. I could probably add it in a better way. It's happening because we have references and you just need special constructors for them. At least I can use the same variable names, so I don't have to think about two different variable names. This is a good feature in C++. Your constructor arguments can be the same name as your members. Break flag or flow flag. Great. Then we have sign flag. Sign flag. Great. Oh, we also have the main method. Great, we have our constructor down and everything should be good from this point onwards. Okay, now what I'm going to do is I'm going to make an entry point for our actual emulation function. So let's return void from it. We don't need anything special. And then we're going to say emulate uh, code, right? And this is going to accept the address where we want to start emulating from. So that's going to be first of all we're going to accept the main memory. So this is going to take char star main memory. This is where like the static memory is stored. Uh, uh, then we are going to accept the address where we want to start emulation from. So it's going to be NES word, right? It's going to be an offset, and this should be good for now. Let's do this for now, uh, and then we will slowly sort of modify this later. So, okay, so we have a function that accepts the memory, it accepts the address, and starts emulating from there. You might say we don't accept the registers or anything like that. The registers and all we will actually be referencing. We'll be creating local copies of those registers and referencing them, and then we will be loading them from memory, from actual sort of like registers. It's a we'll get there. Yeah. So what I need to also do is like have actual global versions of those registers, which I can sort of attach to. So here's what I'm gonna do. I'm going to say extern DNES byte ACC equals. Oh, we don't need a equals here. I'm just gonna make declarations. These are going to be the actual registers we sort of allocate for the runtime. I'll get to why this needs to be separate from the context a bit later. It seems like a lot of like code being rewritten again and again, which it is. I'm sorry about that. But it is all for optimizations. No, and we don't need a D main memory. Or do we? No, we can accept it as a parameter. It's okay. Yeah, so D main memory can be a parameter. So that becomes DNS byte address main memory. Yeah, so have the main memory now. Okay, so we have all our variables, all our register state and all our sort of context defined, and now we're going to actually start executing. Uh, Okay, so this doesn't actually accept any context because the context is created inside the emulate code and then passed around. So as we have multiple functions, they will all accept this context variable. And that way we can pass what register sets we are using, what byte flags we're using and everything without having to sort of like write the code again and again. Okay, so let's see if there's nothing, we haven't included this. So let's make the src emulator.cpp, right? This is going to include emulator.h, right? Uh, let's go to make file and add this to our object files. This usually I do using wildcards, but I think this is a small project enough that this should be okay. Great. So it's saying that we don't have our header files correctly pointed to, so we just go to C flags and we say dash I includes, no, include dir. Sorry. There we go. We have some errors. DNS. Oh, I made a typo there. Invalid initialization of reference type DNS. Oh, types are wrong. So this should be word. And finally, conflicting declaration of DNS byte memory main. Oh, I gave it same name. Oh, it wasn't here. It was. Was it? Okay, that was correct. So, okay, so our headers compiled correctly, no issues. We haven't included. Yeah, we included the. We didn't include the instruction thing, right? So let's include this and see if that fails. We will need the instructions here. Uh, Actually, we don't need it inside the header. We need it inside the emulator. Okay, ISO C++ does not allow C99 designated initializers. Great. So now we have reached the first problem, which is this is an extension. So, okay. What we wrote here is basically an extension that lets us uh, like specify values for specific enums. So what I'm going to do is I'm just going to assume that they are in the right order. Uh, so this is always going to be 0, 1, 2, 3, and so on. We're not changing it in any way. So that means I can, uh, sorry, I can just remove the values and put them as comments. C++ equals to quite a work to emulate decade-old target. Seems like it, yeah. I mean, there is this different size registers and this. Also, we're trying to make a compiler. Compiler is usually a lot of work anyway. So, yeah. What I'm gonna do is I'm gonna strip the things before the equals, so that way we don't have to. Oops, sorry. And now I'm just going to. Yeah. I should probably leave comments to say what this is, but then I have to type everything back and now. I should become better at them. Should be able to do this by some magic tricks. What is am underscore hash? Oh, hash is just the bound one. Yeah. I hope I don't have to do this for more things. I think I did do this for cycles too, right? No. Hmm. Okay. Oh, the names are all certain. But the good thing about names is we don't need to put names, we don't need to put comments for names, so that should be pretty easy. Great. I think the rest is good. Great. We have everything compiling, which is always a good sign. And now we can actually implement our thing. So what I'm going to do first is these are just declarations, so I need to have definitions for them. This is inside names space NES. Don't need the extern anymore. And we need to give these actual names. So I'm going to say builder as global uh, reg_acc. Now, as global is a way to tell builder that this variable is a global inside the first stage, which has some certain implications in how the implementation works. But the main idea is that you can give it a name. So this is going to be a variable that has a name, register_acc in the generated code, which is always nice to be able to debug things. So yeah, so I also copied right statements. Okay. Sorry, there has to be a better way to do this. Okay, yeah. All right, so we have registers. I'm gonna say X, Y. Fortunately, I won't have to write these again and again. They'll be just generated, so that's okay. Uh, Great. So these will be generated as it is in the generate code. That's good. Now we just need to implement our main function, which is the uh, emulate code function. Great. Okay, so the emulate code function accepts main memory, it accepts offsets and dmain memory. What I'm going to do now is I'm going to create a context that directly just references these global variables so that we can pass the context around. So the first thing I'm going to do is NES context D, and then I would have to provide all the parameters. So this becomes, you might say, why didn't I just directly use the globals? That's part of an optimization I will talk about later. And that's it. So we have all our context enabled. And now we can start generating code. So what we do when we have a interpreter for a language that has a bunch of instructions? We iterate through the instructions. So basically simulate the PC, right? So what I'm going to do is I'm going to make a NES, oops, sorry, NES word PC equals offset. So this is where we are starting our execution from. And there's going to be a main while loop, which just says, uh, I'm going to keep on running forever. That's how the interpreters work, right? We'll have a break statement somewhere depending on what happens, but yeah. Oh, by the way, if we actually look at the original implementation, there are a few instructions that actually stop the execution. So I think BRK is one of that. Let's check. I actually had listed it down as one of the instructions to stop at. So if we go to source, yes, Yeah, there's BB end opcodes internal. It's just like the opcodes at which the BB ends. So we have 4C, 6C, and 6D. Um, what are these instructions? Let's look at this. 0x4C. 0 and 4C. Yeah, 4C is jump. So yeah, whenever there's a jump, that's an end of a basic block. 6C is also jump, but indirect. And we have 6D. So no, 60 is going to be annoying to find. Okay, there we go. So it's RTS. Yeah, return from subroutine. If you see a return from subroutine, that's the end of a basic block. Unfortunately, there is no instruction that sort of like just stops the execution. And we're going to need that because our code generation needs to stop somewhere. So I'm going to do what is, I'm going to take sort of like a artistic liberty here and use one of the unused instructions to just stop. Uh, this is not ideal. Also, we won't actually need this for the actual ROMs because they don't have that instruction. But I'm just gonna say, okay, if I reach this instruction, we have reached the end of the execution. You can stop execution here. So that's a sort of a trick we are gonna do. So let's use the last unused instruction, which is this null, and let's say it has let's call it ext. So ext instructions 255 basically says, I have reached execution, please stop. Uh, yeah, that way we can when you're testing our code, we can put exits in the middle. Okay, so how do we emulate this? So we have while one, which just goes over the entirety of the program. We're going to first load what the instruction at this address is. We are going to assume that the PC is always at the point where the instruction starts. So let's say uh, oh, you need to load the byte first, so it's going to be NES byte uh, opcode equals main memory of, it should have been unsigned car. I don't know why I made it. It should have been byte star, NES byte star. Let's change this. Replace this to change. Don't assume your memory is unsigned, folks. It's going to be, your char is unsigned. It's going to create issues. Okay, so we're going to do NES byte opcode equals to main memory of PC. So we load the value from the PC. And now we sort of do a decode on this. So how do we do a decode? We just do NES instruction T instruction equals, going to get a 6502 kit and hand code all the code with the help of your 6502.txt. Yeah, I'll share the. I didn't write the 6502.txt. I found it somewhere, but unfortunately it was 6 years ago, and I did not document where I found it. But there are ways to. Yeah, I'm sure you can find this somewhere on the internet. But yeah, I'll write it. And yeah, if you get a 6502 kit, I would love to like just look at it how it yeah works. NES instruction T equals to just now we just like dip into this instruction. So just say NES instructions. Actually, if you close this, yeah, yeah, it's just NES instructions of 256 size. So we're just gonna say uh, NES instructions of opcode. Great. So we just got what the instruction is. We can print it here if we want. So uh, let's do printf. Uh, actually, you know what? Let's not do printf for now. Let's do a proper execution. So let's say if uh, we need to actually check what type of instruction this is, right? So let's simulate them one by one. Let's simulate with beginning with uh, the load because that's the easiest one to usually implement. It just goes and loads the value. But we'll have to implement all the addressing modes for it. So that's where it gets fun. Yeah, so the first instruction is actually let's do load LDA, right? So it has all the addressing modes. And the good thing is our table tells us what addressing mode it is. So we just can dispatch based on that. So okay. I can't use a switch case because we use strings for this. If we had used an enum, it would have been nicer, but I got lazy and I used strings. So let's do if. If I had used string, that would have been easy to compare to. Actually, you can cast them as string, so that should be fine. So I'm going to say if std string of instruction dot name equals LDA, then we have the implementation. And for all the else, I'm just going to say invalid instruction and break. So I'm going to say return here, and I'm going to print an error message. So std error invalid instruction opcode, right? This way we can like debug it later if we have to. So right now we are assuming that the only instruction that we have is LDA. Now we have to check what the addressing mode is. So what was the struct for that? We have addressing mode T. So actually, let's make a separate function. Let's say LDA needs an operand, right? So we're going to make a function first, which gives us what the value at that operand is. So it's going to be d word, NES, d NES word. It's gonna usually these no wait addresses operands are just bytes. So it depends on which instruction we're using. LDA needs a single byte, so I'm gonna say uh, equals load byte. This is going to require the instruction itself. So I'm going to pass because like if the addressing mode is immediate, it could have the value inside. If the addressing mode is sort of indirect, then it's going to load from the memory. But either way, it needs to know what the instruction itself has. So we need to pass it the bytes of the instruction. So it's going to look like main memory of PC, take its address. Right now, look at this. This returns uh, 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 this returns DNES byte. So it's not actually executing anything. It just like in the second stage, this will return us what the data is, and then this is going to need. We have already decoded the instructions, so might as well give it to it. Right? This loads the data. And now I'm going to say context. Actually, this needs the context. This is where the context comes in handy. So we say context. We always pass the context so that if that needs any operations, if it needs any flags, everything is available here. And what does LDA do? LDA just says context of, uh, what do we call it? Accumulator? ACC, yeah. ACC equals data. So we're just going to set the context to be data. This is essentially going to set the global variable regular reg underscore ACC equals data, which is nice. Okay, so now that we have done this, we need to implement the load byte function. So I'm going to say DNES. It's going to be a static function because this doesn't need to be exposed to the user. Uh, Load byte NES context, sorry, context D context. Then we need NES byte star main, no, yeah, instruction. And then we need actual instruction, the instruction. Okay, so let's implement all the addressing modes here. So let's do a switch case on this now. Switch instruction dot addressing mode case. What addressing modes do we have? Let's do, what is A? I thought we have absolute, absolute X, absolute Y. Actually, let's go this way. Yeah, so we have, let's do start with immediate. Yeah, let's start with the immediate one. In this mode, the operand's value is given in the instruction itself. So LDA 0, 1, right? So let's do this. So uh, case, what do we call it? AM underscore I. I think this was A was immediate. Is it? Let's verify. Yeah, so LDA opcode, we want the immediate one. So this is here is A9. What is A9? 169. Okay. Okay, so LDA hash. Oh, hash was the immediate one. Perfect. There we go. Uh, AM underscore hash. Okay, so if it is an immediate one, we have been given where the byte is located uh, in the instruction. So we can skip over the opcode first. So that we should do anyway. So we should say instruction plus equals to 1. It's always going to be 1 byte opcode, so we can skip over that. We don't care about it. And at this value, we have a byte of data stored in memory. We just have to load that from the instruction. So we say return uh, instruction of 0. That's it. This gives us what that byte value is, and it always loads a single byte if I understand correctly. So immediate, uh, yeah, loads with a single value. Perfect. So that's what we wanted. So we got that instruction working, and what I'm gonna do is just gonna say default again, sort of a similar error message, invalid addressing mode, uh, invalid, but eventually we'll fill up all of them, so it's fine. Addressing mode. Instruction. Uh, Putting a return here is not enough. We actually have to exit. So I'm gonna just use assert false here. Also put a return 0 there, so that if you're disabling debug symbols, debugging, then the assert still like it still executes something. You can actually put a return 0 here, which should take care of everything. Okay, so we have our default addressing mode and we have one LDA instruction written down. Let's just test this out. Before we go ahead and implement all the instructions, we should test this out. So first of all, does this even build? Obviously it doesn't build because what did we do? Okay, STD error is fine. We'll fix that one by one. Instruction T has not been declared. It was inside the instruction namespace, right? Yeah, instruction. It's okay, we can do it. Maybe it was not that good of an idea. Is it NES instruction T? What did I call it? NES instruction T. That's the only place this type was used. That's good. Now it says, conflicting declaration. Oh, I just used the same name. Perfect. Okay, AM hash. Did you mean NES instruction AM hash? Of course, because it's inside the namespace. So this needs to be. This we can fix. ERR was not a member, so this needs to get. Oh, CLL. What am I writing? I've done too much LLVM. Sorry. This is what happens. LLVM has a stream called ERR where you can dump out messages from the compiler, and I was using it's just stuck in my head. Okay, no matching function call for this. 12's to provided. Okay, I missed some arguments. But yeah, I should have provided the address and stuff, right? I didn't provide that to the context. That is right. It needed the main memory and the D main memory. Perfect. NES instructions of opcode. That should also be inside the namespace. Hopefully this is a one-time thing. I won't have to do this again and again. Perfect. We have our instruction thing working properly. We are like sort of generating code now, basically. Uh, what I'm going to do is I'm going to write a simple program to make sure that this is running correctly, right? So let's instantiate a piece of, okay, we forgot one thing. We need to put a exit instructions. Otherwise, this is going to completely crap out because it's going to keep on running in a loop. We don't want that to happen, right? So I'm going to add a else if. Actually, you know what? I'm going to do this. std string name equals instruction. Like this every time. Okay. Else if name equals ext, which is the instruction we use to say that I'm done executing the whole thing. I'm gonna just put a return here. That's it. There's nothing fancy need to be done. We just if you see a thing, we just exit. Great. Make sure that everything runs. And it does. Okay, so now let's write a simple program where I'm going to create a program in memory and then try to sort of generate code for it. So what do we need for this? What does our emulator need? It needs uh, a, a sequence of data, a sequence of bytes where the data is stored, and the offset to start are. And everything else is a D argument, which means we don't need to supply it. It's going to be provided at runtime. So let's see what we can need to do for it. So we can say char star, actually no char star, just let's use the proper type. D NES NES byte program is an array equals, we're just gonna put some two values for now, but I'll fill those up later for what we want to emulate. And then I'm gonna say the offset is gonna be 0. So NES word offset equals 0. We're going to start executing from the first offset in memory. Later this will change because when we load from the ROM, we'll have to figure out where the execution starts from, where the actual data is loaded, and that moves around. So I'm just thinking forward a little bit. Okay. And now we're going to do the actual BuildIt thing. So I'm going to say, oh, I need to builder, builder underscore context dot h. Okay. And now I'm going to make a context. This is not the same context as we made before. This is a BuildIt context. As you can see, I have a very bad habit of naming types similarly, but yeah, this is a builder context. So now I'm going to say context.extract function AST, which is usually our entry point for all the things. And then we say auto AST equal. This returns the program that we are creating. What this takes as arguments is the first is the actual program you want to execute. So it's going to be emulator, it's going to be NES colon emulate code. So this is the function we want to sort of specialize. And now we need to provide the name of the generated function. So let's just say run code. This is what we want the generated code to be called. And finally, we need the argument. So this is going to be the program, and it's going to be offset. Unfortunately, this doesn't decay by itself, so I'm going to do this. Yeah. this should take care of it. Great. Now we have our program generated. I just need to generate the code out of it. So I'm gonna say uh, hash include blocks C code generator dot h. Good. And then I'm gonna say block C code generator generate code. It takes the AST, it takes the stream, and it takes the initial indentation. Okay, let's see if this compiles. It doesn't compile because I forgot to use the namespace. I feel like this is being repeated a little bit, like NES colon colon NES should have just been like byte and word, but I get scared using names like that. NES has not been declared, yes, because we have to include it. So I'm going to say include uh, emulator.h. Perfect. Did you mean NES? NES, right? Yes, I didn't mean that. There we go. Our code compiles. Now I'm gonna try putting a program. So the last one should definitely be FF because we want the program to stop, right? We want our what we have done here is the last instruction is ext, which is 255. We want the program to stop when it reaches there. Let's look at what LDA is. LDA immediate is the one that we're going to try to simulate and see if it works correctly. So we are going to use yeah, here's our table. We have LDA immediate, its opcode is A9, so that's what we're going to do. And it takes 2 bytes and number of cycles. Of course, we have not done the critical thing that we needed to do, but we'll get back to that. And then, so let's put that instruction here. So let's say it's A9, right? And then it takes 1 byte of the actual data to be loaded. So I'm going to say 0x, what's the data? Let's say AB. I want to load AB as the data from the instruction. This is our 2 byte instruction, which brings me back to we never incremented the PC. We just did the thing and then we went ahead. But we should increment the PC before we go ahead. Otherwise, we'll be stuck in an infinite loop. So become PC equals to PC plus. Let's what was our instruction thingy? The base cycles. Sorry. uh, base cycles. Yeah, so this is going to tell us how many cycles this takes. Sorry, that's the cycles. We need the number of bytes for this. So uh, sizes is what tells us, based on addressing mode, it tells us how many bytes this instruction is. So in hash here is 2 bytes because 1 byte for the opcode and 1 byte for the actual data. So what I'm going to do here now is PC equals to PC plus instruction dot addressing mode am underscore sizes, but this time I'm going to put the namespace. There we go. uh Perfect, it compiles. What I've done in the driver for now is I just wrote a dummy program with one instruction followed by the exit opcode, and then I put in pass this to the BuildIt, and finally I asked BuildIt to generate code for that AST and print it out to the stdc out. So it will just print out the code that we are generating. Let's try running this. Let's see what happens when I run this NES compiler. And great, we get some C code. What the C code is doing is it has run code as a function. So let's actually look at this side by side, right? Uh, Actually, this goes here, this goes. Yeah, so side by side, we have this run code function. It's called run code because that was the name we specified here. Its types are automatically inferred. So its types are inferred from the function that you passed here. This function returns a void, so it returns void. And it takes 3 arguments, two of which were normal C++ arguments. So those are not in the generated code, but it had one, if you look at it, it had one D argument or dynamic variable argument that gets produced as it is, which is what is here. This argument is basically the address that will the memory that will allocate for the runtime code. And then inside it, it just has a bunch of instructions, the actual implementation of those instructions. So this is char star var 0 equals to R2. It's just moving the memory into a separate variable for no reason. We will optimize this later. And then it has unsigned char var 1 equals to 171. So the 171 is here the value it load from the instruction. So we had written our instruction to be 0A9 0xAB. So AB here is the bytes that it's actually trying to load. And if you look at the byte representation of 0xAB, it's 171. So it loaded at 171 into this unsigned char, and then it assigned regACC equals to var1. Now the problem is, what is regACC? It never actually came up. Like, where did we define this? So that's the other part we need to do, which is at runtime, if we have some global variables, we need to spit those declarations and definitions out. So that's what we're going to do next. We're going to need declarations for all the registers that we created in the generated code. But instead of doing that, what I'm going to do is I'm just going to create a header in the runtime that has these like the definitions and everything. So I don't have to like change the code generator for it, which basically means I just do this std cout hash include let's say runtime.h, right? That's basically what it is. And then std Kindle. So the generated code, whatever needs, we can provide it as part of this runtime.h, which means I need to make it, but I'm not going to make it inside the include directory because our written code doesn't depend on that. It only depends on the generated code. Uh, so let's do runtime slash runtime.h, which is a bad name, but I think it should be fine. And then if and if and if Uh, and this is just going to have a type def unsigned char star. This is C code now, by the way, at this point. So we have to be very careful mixing languages. Oh, what is happening? Why is it not going to save it? Oh, I don't have a directory called runtime. Great. And now I'm going to say nesd word reg acc. Actually, you know what? Let's copy stuff from here. I'm going to accept this. We don't need this anymore. Okay, so we had our actual registers that we had created. Now we need to uh, so NES word, NES byte. Wait, why is it D word? It should be NES word. Yeah. Uh, so, so did I name this correctly? Did I make it short? Yeah, it is short. Perfect. So now we have these, which means I can just delete these. So we don't need the D anymore. This goes away, and that's it. So we have our declarations now. Oh wait, this should be external. What did I do? So we have our variables declared that we will be using. Okay, and let's just make a sanity check if this compiles. So NES compiler, this prints out the code hash include runtime.h this time, and it compiles. So what I'm going to simply do is I'm going to make a scratch directory first, and then I'm going to try to compile it this code. So scratch c gcc scratch t.c dash o dash t. So it doesn't find the header, so we just give it, and there we go. So it says a reg acc undeclared because I did not put reg acc here. Wait, which one did I copy then? Oh, the names are different from. I hope I named them correctly. reg flag C. And okay, that's good. We don't let's see if this just compiles. We don't have to link it. There you go. So it compiles. We have correct code being generated, and hopefully it does the right thing. Now we just have to implement a bunch of other functions, and it should work. So to look at the code that we had produced, we basically have a code that sets the register accumulator to var1, and that's what we wanted. Uh, we will further optimize this. We'll make the variables local and everything. That way we don't have to access global variables all the time. Uh, we'll look at the performance and see how it goes. Anyway, so this is good. Now we can add a few more addressing modes. Let's actually add all the addressing modes. So what's the next addressing mode according to 6502? Okay, so we did immediate. All it does is loads the value. Then is absolute and zero page absolute. So in this mode, the operands given is the address is given to load it from. So I'm just gonna uh, yeah. This is straightforward. Again, we just have to load the value at whatever. It gives you a 2 byte value. You have to load the value from there. Okay, so let's say let's do case instruction am underscore absolute. Right now, we have the value. We need to get the address first. So we say uh, the address is gonna be known at runtime, but we know the absolute values. So we know the address of where the data is located in this one. So we're going to say d word, yes, word, uh, adder equals. Okay, so this is encoded in Little Indian, if I remember correctly. The encoding is the low byte is stored first. Okay, so F631. Um, the good thing is we can make it as slow as we want because this is happening in the first stage. We don't have to worry about like instruction decoding happening in the wrong way. So we can just do instruction adder equals instruction. Let's take the first byte, shift it by 8 bits, and then OR it with instruction adder of 1. So we take the 2 bytes and we sort of OR them together. Did I do it the wrong way? Yes, I did it the wrong way. So this should be 1 and this should be 0. We take the first byte, which is the lower byte, and then the higher one is done this way. So now we have the whole adder. And now we do, oh, this is going to be a problem. If I shift this by 8, I need to do first why do I keep adding D word? NES word. I need to cast it first before I do the shifts. Otherwise, uh, it's gonna overflow. Okay. This is gonna give us just the address. And now we just say instruction of context dot d main memory. This is where the data is actually stored of adder. Right? Makes sense. We just this is absolute addressing. We got the address from the instruction, then we use that to index into the memory. Let's try it out. Let's say this is instruction absolute, by the way. So let's put that as an instruction. You know what? I'm just gonna indent this so like debugging is easier. Okay. This is the first instruction. This is the second instruction. And the last one will always be this. So, okay, what's the second instruction? What is the LDA absolute addressing mode? We're going to test all the addressing modes with one instruction, and then later when we all add all the instructions, we won't have to like create all the combinations because yeah, they all get cross multiplied. So absolute is AD, and it takes 2 byte address. So let's test it out. So 0xAD, and the address I'm going to load from is just 000x FF, suppose. So the last it should be the other way. Zero, zero, zero. So yeah, we're loading from the last address on the first page. That's basically what this is saying. Let's test it out. It's telling us that I forgot the NES instruction. Absolute, is it? What did I call it? ABS. Jump to case label. Hmm. Just I didn't add a break. No, that shouldn't be the issue. Let's look at it carefully. Uh, in function load byte. Jump to case label. What? Did I forget a bracket or something? This looks fine. Okay, so something here is causing the issue. Cross initializations of the. Oh, okay, 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 okay. I should not initialize variables inside switch cases, which is part of the problem here. We'll reuse it, it's fine. That's not the reason, is it? Oh, turns out that was the reason. That was a very cryptic message. Jump to label default. Anyway, so this is working. Now let's test it out. Uh, and there we go. We have a while loop for some reason because let's get to it. Okay, so we have our first load, which is correct, and then we have the value being set, and then it says unsigned char var 2 equals to var 0 of 255. So it's loading the value correctly, and then it's setting the register ACC equals to var 1. Okay, so here's the first mistake we have made. The mistake is here. So we have this while loop which keeps executing things again and again. BuildIt sees that, hey, the execution went back to setting register ACC equals to var1, and I've seen that before. Nothing has changed. If I keep executing from this point onwards, it's going to produce the same code again and again. So I'm just going to put a while loop. But that's wrong. That's because we made a mistake. We declared this PC as NES word PC. The right way to do this is to make it into a static variable. So all first stage variables, if they are changing, they need to be marked as static. If they're not changing, if they're just going to be fixed or there's a constant for the duration of the function, then you can use normal C++ types, which is what we have done for main memory, which is what we have done for contents of main memory. But PC is changing along the execution. So we need it to be set to be static. So, and that should, I think, fix this. And there we go. We get our correct code, which is we load 171 into the register, and it's assigned to regacc, and then we have a load from var0, which is the memory, the address that we get of 255, which was the absolute address at which we were loading from, and we assign the register equals to var2. So that's correct. We have the absolute addressing correctly done. Let's look at what the next addressing mode is. If there's any question about what we just did, please ask in the chat. I'm happy to explain. Uh, let's do zero page next. Page is also the same. It just takes one byte address instead of more. So that should be easy too. It's just am underscore zpg. Uh, Case instruction am underscore zpg adder equals. Okay, so first we have to get the adder. This time it's a single byte. So I'm just going to say instruction adder of 0. Uh, and the higher bits are just 0. So that's okay. We can just keep it like this. And then I'm gonna say return context.d main memory of I. Perfect. We don't need anything else. I'm gonna check this. So the zero page one is A5. And let's this time load from F2, suppose. It's because it's zero page, it only takes one address, one byte address. And there we go. We load from 242, which is F2, and set it to the register. Now, you might see some obvious optimization opportunities here. It's like we're assigning to the register ACC again and again. Do we really need to? And that will save us some loads and stuff. And yes, but here's where the backend compiler comes in handy, right? The C++ compiler sees this and says, hey, you have a bunch of things that when we compile this code, the C code, the compiler sees that you have some useless assignments. I could get rid of them for you. And that's where sort of like efficient code generation will come in handy. Let's actually test it out. Let's put this into scratch t.c, ecc-o3. Uh, okay. And now let's look at objdump. We only have three instructions. The first instruction is loading F2 of RDI. RDI is the argument. F2 is the offset 242. It's loading into EAX, moving that one byte to 00 RIP. This value will be passed later by the linker. This is the global variable regacc. So that's it. It got rid of all this crap for us, which is loading 255, setting this 171, and we just got the shortest possible instruction for this program, for this whole program. And this is why I wanted to generate C code. That way I can make use of all existing compiler optimizations to optimize my generated code. I don't have to optimize these instructions by hand. Normally if you do this by hand, you have to like sort of look ahead and see, okay, is this A is gonna be used again? If not, I can put this instructions, otherwise I can put this instructions, and so on. This lets us like use a compiler to do those things for us, which is great. Okay, so yeah, let's get back to implementing more stuff. We are at 12:10. We are halfway through the stream, so that's a good point. We can like add more implementation. Let's do absolute x and absolute y. I need to look at the specification for these before I mess up. So absolute and zero page absolute, that we have done. Let's do uh, implied. Implied is fine. Implied doesn't need anything. Indexed and zero page indexed. So indexed and zero page indexed. What does this do? Uh, it's just a absolute value. In this mode, the address given is added to the value in either the x or the y index registers to give the actual address of the operand. So it's like absolute, but x and y is added to the value before it. So that should be easy. Uh, let's copy this, and they also have a zero page version, obviously. So indexed zero page, indexed and zero page index. Okay, so I call it am underscore Index? That's indirect. I think it's absolute X and absolute Y. Yeah. Okay, so this gets the same code as the first one, but it just gets added. Instead of adding here, I'm gonna add it here. It'll be context dot uh, X-ray. Is that what we called it? Yeah, X-ray. This one I actually need to test before I move on because this is sometimes tricky to get correctly. Okay, so we have adder equals, we load the adder from the instruction and add xreg or yreg to it based on the addressing mode, and then we return the value from the memory. Let's see if it compiles first. It does compile. And let's look at, actually I should put a mark there. Come on, I keep doing this. Okay, I have a mark here now. This should be easy to go back and forth. So absolute X is what it is called. Yeah. Let's do BD, and then it takes 3 bytes. Great. So 0x BD, and then 0x F2 comma 0x03, suppose. This is the indirect X, sorry, absolute X. There we go. So we have xrect plus 1010, which is, I'm assuming, correct. 03F2. Yeah, this should be fine. Yeah, so this is working correctly. We have x reg plus 100, and then I'm assuming y reg will also work correctly. B9. Eventually, the code will all come from the ROMs, so we won't have to write that by hand, thankfully. Okay, and this is working fine too. Great. We have the 4 basic ones done. What is next? We have the zero-page versions of these two, I'm assuming. No, they don't have a zero-page version, do they? There's a zero-page X. There's no zero-page Y. Not sure. Is that correct? In the zero-page version, you should note that the X and Y registers are not interchangeable. Most instructions which can be used with the zero-page indexing do so with X only. Okay, so I guess this doesn't support Y zero-page indexing. Okay, so let's just implement that. This is gonna be like this, zero-page underscore X. And this just get reg. It's context.xreg. Yes, and I think that should be good enough. I'm gonna leave a label here too. As the zero page XB5. And there we go. We get our xreg plus 242, which is what F2 was, and this is perfect. We have all our instructions being written correctly. Let's go to the next addressing mode. Okay, we are left with absolute indirect X and indirect Y. So let's go and see what those addressing modes are. There is a separate index, but that we don't need for the, that's only required for jump. We'll get there when we get there. We need the pre-indexed pre-indexed indirect. So there is pre-indexed indirect only works with X is what I'm assuming. Okay, wraparound addition is used. That is, the sum is always zero page address. When adding the 1 byte address in the X register, oh, that's for zero page. Okay, but we're not doing a zero page version. Oh, it's always zero page. Interesting. Okay, so it says in this mode, a zero page address is added to the contents of the X registers to give you the address of the byte holding the address of the operand. The indirection is indicated by the parentheses in the assembly language. Okay, and then it says when adding the 1 byte address in the X register, wraparound addition is used. That is, the sum is always zero page addressed. Interesting. So FF plus 2 gives you 001, not 0101 as you might expect. Only the X register is used in this mode. Okay, I guess we're doing this then. What is that? X indirect. EM underscore X indirect. This takes a zero page address. I'm going to copy this one. Uh, X indirect. So the address in this case comes from, okay, I'm going to make a, fortunately it doesn't allow variable declarations here. Maybe I could. So, I need it. I need it. Okay. Um, so this gives us the first index, which is the first part, and then we need to do, yeah, let's put a block here so that way I can declare variables locally without C++ complaining about it. So I'm going to say NES DNES word in this case equals adder, no, first, oops, sorry, what did I do? DNS word adder adder equals reg context dot xreg plus adder, and then don't forget the modulo. So modulo 256. The first page is always 2. So this gives us the first address, and then that's it, right? Yeah. And then we can use the return d adder instead. Let's first even check if this compiles. I'm worried about that curly braces. Okay, that worked. Yeah, so the hack I'm doing here is because C++ doesn't like local variable declarations inside switch cases. It is, I'll have to hoist the declaration up. But if I do that, it's going to, like, at least for the beginning, when we don't have optimizations, it's going to produce like a lot of variable declarations everywhere, which I don't want. So this is just easier. And this should do it. Let's test it out. So we have indirect XA1 and it takes 1 byte. So let's actually do a bigger value. Let's say, all right. So yeah, when we compile this, we get unsigned short int var7 equals to reg x plus 245 modulo 255. So we take x, add 245 to it, which was, wait, was it 245? Yeah, I've used f something. And then we do unsigned char var8 equals to var0 of var7, and then register accumulator equals to var8. This works, this looks fine to me. Uh, let's do the addressing y1. I think that's a different, um, it's pre-indexed indirect. No, that's post-index indirect, sorry. Post-index indirect again takes a zero page address, dereferences it, and then adds y to it. Here the y is properly added. There's no wraparound or anything like that. And yeah, this looks fine. This should be similar to This, I suppose, yeah. Uh, Actually, I don't need the curly braces here. No, I don't need the curly braces because I need to load the value from the main memory. Wait a second. We just added the register to the offset. You're supposed to do context.b main memory. It's an indirect access. We forgot about that. Yeah, but this is only going to give us 1 byte, right? We need 2 bytes. I'm gonna have to check this again. This is slightly confusing. So we have in this mode, zero page address is used to the contents is added to the contents of X registers to give the address of the byte holding the address of the operand. Yeah. So no, wait, this is fine. This is fine. Now, how is this different from the absolute X then? There is definitely double indirection here. In this mode, a zero page address is added to the contents of the X register to give the address of the bytes holding the address of the operand. The indirection is indicated by. Yeah, there is a double indirection here. So, address of the operand. Yeah. So this needs to be okay. So this is going to give us 1 byte. We also need the 2 bytes. So and we have to make sure that it's stored in little endian. So how to do this? Okay, let's do adder one and adder two. Um, so this gives us the address that we have to be careful about the wraparound. If the first byte ends, oh God, this is so confusing. Uh, when adding 1 byte address in the X registers, wraparound addition is used. The sum is always a zero page address. This means that if the first byte is on the end, the wraparound happens in for both the bytes, not just for 1 byte. So okay, so this is gonna be that means we don't need this. So it's context. This is the higher address, right? Yeah, and this is the low. And for the high, I'm gonna do context X registers plus address plus 1 modulo 255. So the high byte comes after, the low byte comes before. Is that right? High comes after, low comes before. That looks correct to me. And now I'm gonna create the actual adder. So it's gonna be dnes word the adder equals the adder of high shift 8 or the adder low. So now you have to see that this code is actually going to be generated. It's not uh, executed, and we will test that. Okay. Okay, so we have two addresses uh, loaded from different locations. Then we actually OR them, and then we use that to load from the memory. Okay, this looks correct to me. Now you might say, is there a better way to load this? Can we make use of the fact that our addressing is also like our so host addressing is also like the same Indianness. Usually yes. The problem is this offset could be like this whole thing could wrap around, and I don't want to. Yeah, if this wraps around, the first one wraps around, the other one doesn't, then we have an issue. The way to handle this could also be like have a if condition in the generated code, but I don't think it's worth it. This load should be fine. And but some of the other loads we could take care. Like if there's a two, but we don't have 2 byte loads. This is the only 2 byte load we have, so it's okay. All right. Okay, so then we have the indirect Y. This is the other way. First, we load from the zero page address the byte. So usually this comes. Okay, we get the 0 byte address. Uh, the xreg or yreg is not added here. Yeah, this is now where you could put a condition. You could say if this if the absolute value you're loading from is not actually wrapping around, then do a single load. But the good thing is the compiler will take care of that for us, the backend compiler. So we don't have to do this. We will test it out. We'll test it out. And then this becomes uh, just to yreg. Find the instruction encoding for that. Y indirect is B1 and takes 2 bytes. Let's try different cases. Let's see the wraparound works properly or not. I'm assuming that there's a wraparound here. Does zero page addressing have a... Oh, actually, you know what? We didn't check that. Does zero page addressing have a... Oh, you're loading a single byte. That's okay. Okay. It's because we're loading 2 bytes. That's where it's a problem. These are one of the hardest ones to implement. Post indexed. In this mode, the contents of the zero page address in the following byte give the indirect address which is added to the contents of the Y register to yield the actual address of the operand. Again, in assembly, then okay, this is fine. I think this is correct. We will test this if it's like this is it says the following byte. Now this following byte should actually be with the wraparound, so I'm sure it's with the wraparound. And we could also check my old implementation to see what it is. Actually, you know what? Let's just do it right now. I'll feel. Uh, so this is gonna be in source x86 translation, and I have indirect underscore y. Yeah, so read indirect y. Let's see how we implemented that. Jesus, this is hard. Uh, Interesting. We did not actually do so we load the value into R8, we increment the address, then we load R9, and then we shift and add them. Oh, we did not actually do a wraparound here. Yeah. Oh, no, 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 sorry, sorry. INCB. Hmm, confused. Actually, yeah, INCB will do that. INCB is incrementing it just the byte. So yeah, this will do the wraparound. Yeah, okay. So we did the right thing. Great. That completes our indirect addressing mode. Did we miss anything for this one? Okay, so load has covered all the addressing modes. Immediate 1, 2, 3, 4, 5, 6, 7, 8. 8 addressing modes for this. Have we completed all of them? 1, 2, 3, 4, 5, 6, 7, 8. Perfect. We have all the 8 addressing modes for load done. Now let's add the next instruction. obviously after load, we need store. So let's do, wait, what the hell is it? LDX, that's a separate instruction. Um, oh, by the way, load also sets some flags. So let's take care of that. Uh, it sets the N and Z flag. So let's see what those are. So the N flag is set if Z, I understand. What the hell is those flags? I think it's described here. Yeah. NZCI. Okay. And Z is zero, C is carry, I is interrupt, T is decimal, V is overflow, and N is what? What is the N flag? Oh, I don't have an N flag. I'll just look at my old implementation now. What is this flag? Set N and set Z. Set N. Not negative. I see. Did we have that? Did I miss it? Oh, the sign flag. Okay. I've used commonly used flags names are CZVS. Then okay, sign flag. This is set if the result of an operation is negative, cleared if positive. So we just need to add that. The LDA implementation. So what we're going to do is also make a function for this that's easier to call from different things. So I'm going to say set n. We're going to call those functions specifically that only those flags that we are touching. So this could also be encoded into like a table nicely. Hello, I'm Fanberg. What are you doing? I am working. Sorry if it was an old message. I'm implementing emulator sort of compiler for the NES Nintendo Entertainment System using BuildIt, which is like a multi-stage programming framework, and using it to write a compiler, hopefully an optimizing one. That's the two-line gist of what we are trying to do today. Yeah, so we need to set n. So that takes our context. Context should be good enough. Yes, context, we context. So all this should do is if context dot reg, actually no, the register, it's not just the register, it's the output. So we're gonna take the output. DNES byte output. Uh, we can use the reference here, that's fine. If output is less than, okay, what was the explanation for it? Sign flag. If this is set if the result of an operation is negative, cleared if positive. I see. If output is less than zero, then context dot uh, reg flag s equals one, else context dot reg flag s equals zero. Yeah, so this is just what I guess sign flag. Wait, we do not have the conditions. Uh, where are you from? I am currently in Cambridge, Massachusetts. I'm a PhD student here at MIT. I grew up in India and I've been here for 5 years now, going into my sixth year of PhD. Yeah, I grew up in India and I'm here in Cambridge, Massachusetts right now. Okay, what did I? Oh, I did not call the function. So we go to MBA. After we have done all the things, we do set n, and we tell it what we're setting it with, and we need to pass it the context. Actually, you know what? Let's keep it same. Let's keep the context as the first argument. Great. In the same way, we're gonna do all the. Have you ever worked with Lua? I haven't. My most of my research is on C++. Plus plus. I've used a few other languages, but I've used Lua in very like in some classroom settings where I was taking some courses, but that's about it. Yeah. Okay, great. So now we have a bunch of conditions being generated which check if our value is negative, and if it is negative, it sets a bunch of flags. Don't worry about this. The backend compiler will optimize this. Let's see how it does it. But I'm curious why you're asking about Lua. Is there have you seen an NES emulator or something written in Lua before? If you have, I would be curious to look at it too. Uh, yeah, regex and reg y was not declared. Let's see what our runtime. Anchor input file unused because linking is not done. Okay, I did not use a linker flag though. Oh, that's fine. Okay, obj dump. That's weird. So let's look at this. Should we use O3 for it? Compiling. I did use O3 for compiling. So there's a bunch of instructions being generated. I'm not just surprising. I would have expected to just like optimize the previous instruction, but apparently not. Oh, so this F2 is still here. I think it's the conditions that are causing it to. But either way, I think we can deal with this later. There are ways to tell the compiler that hey, you don't need to. I think the part of it is we are also modifying the global variables, which is constantly like telling it, okay, there is some writes on data, and I don't know if I can optimize it correctly. There's like bunch of interleaved writes, and it doesn't know anything about where those writes are overlapping or not overlapping. So maybe it's just like, okay, I'm not gonna yeah. Yeah. So it gets the part of the reason is the address that it gets from the memory. It doesn't know if this is going to overlap with any of the global variables, and which is why it won't optimize it. That there are ways to tell the compiler that hey, this is not going to overlap with anything. You can either do that, or we can make those register variables local. And once we do that, everything just becomes easier. Maybe I do that right now. Oh no, you know what? Let's just implement more instructions first, and then we can get to optimizations. Okay, let's go to the next instruction. So we just did LDA, which is loading values into the accumulator, uh, and then we set the N flag for it, we also have to set the Z flag, which, if I remember correctly, just checks if the value is zero, right? Zero flag. This is set to 1 when any arithmetic or logical operation produces a zero result, and is set to 0 if the result is non-zero. And we know that LDA sets n and 0, so that is great. So we don't need any more, hopefully for now. So this is output equals to 0, then context of sign flag, or in this case, 0 flag equals to 1. Zero flag equals to 0. Perfect. The compiler will optimize on how these flags are set. It will probably not produce jumps uh, if we are lucky. I did not call set 0, did I? The reason I'm keeping it in the function call for now is there might be some different behavior in how those flags are set for other functions. So I'm just going to manually call which instructions do what. Okay, this looks fine. So if we have 0, then the 0 value is being set. Uh, and this looks good. This will get optimized. Don't worry about it. Any of those jumps? Yeah, there are no jumps. There's just like yeah, there's just, let's look at the last one. So this is the address creation, ESIRAX, adding 1. This is storing the value of the accumulator. Then it does this. Yeah, it's not producing any jumps. That's good. It's going to be straight line code for us. Great. So we have optimized code for this. Let's see if we missed anything from LDA. We did not. Now let's go to store. Hopefully this will be very straightforward because everything, all the addressing modes and everything are going to be exactly the same. All it does is the reverse of LDA, which is storing A back into M. So storing the accumulator back into M. That should be easy to add, right? Else if name equals SEA. Just gonna copy this first. So, okay, so in this case, we need a load byte. We also need a store byte. Uh, because load byte and yeah, so yeah, it's just gonna be the opposite of this. It's the same addressing modes, but instead of doing a load, it's gonna be doing a store. So that's fine. We could have changed it to return a reference to the value we are reading or writing, but I don't think we need that. I think this should be fine. Uh, So store doesn't have immediate. Yeah, store doesn't have immediate. You can't store a value back into the instruction. That doesn't make sense. So it shouldn't have hash. It should have ABS, in which case, okay, so this first of all doesn't return anything. It just stores the value. And the value it's gonna store, we're gonna set it here. It's gonna be PNES byte data, right? Um, Perfect. And then instead of the return now, it just becomes equals data. The store is just up. I could have like, I can modularize this in a way that I can make a function that just returns the address as an index, and then the loads and stores can just be like two wrappers on it. Uh, I think it's fine for now. We'll get there when we get there. Um, I don't think we have to re-implement these things anyway. They are going to be fixed, so we should be fine. Oh, I need to add breaks everywhere now. go. What I'm gonna do now is it looks fine. It's perfect. Uh, let's this compile. Else if okay, so this is gonna be store byte. This is gets context.acc. All right. Do you have okay? No, I'm just gonna read the message. No, I haven't, but I was just curious if you've used it before, since not many people have gone out of their way to use it in a larger project. Uh, I would like to. I'm a PL PhD, so programming languages and different aspects of them are always interesting to me. But most of my research is focused on like high performance stuff, and when I say high performance, it usually means different things to different people. Mine is very low level in that like we try to do constant factor optimizations for a lot of applications, and we haven't actually used Lua in any of the code that we have written. Yeah, but in the future, I would definitely be interested to look at it. Do you have any thoughts on the fact that we choose text as our method of communicating to compilers? I find it a bit arbitrary personally. Uh, Text is is one of the most popular medium for communicating with the compilers, but not the only way, right? Like we have had compilers like Scratch, and I mean, okay, I think it depends on how you define a compiler, right? Uh, like programming languages compilers, sure, most of them are text-based, but Scratch is an example which is not. But even then, like if you think of your like some mock tool like that basically lets you write some or think about the WordPress, right? You don't necessarily write code for it. You design some layout on your web interface and it produces HTML for you. That in my mind is a compiler. It does some things internally to translate those representations, and I think yes, the compilers cover a broad spectrum. But I understand your question. Your question is about like programming languages and why most of them are text based. I think it obviously naturally came out of the fact that when programming languages were created, text was the only interface available. But also, I think it's more natural in some way because you can have a larger context in your mind when you're looking at code like text. You can sort of focus in on one, but like imagine if you program with something that's like visual, like if you have like graphs and lines going all around which represent your logic of the flow. That's again, maybe that's not what you're referring to. Maybe you want something even more abstract. The problem is you will eventually like not be able to keep the things into your context. It'll be harder to keep things around. That's my guess. Again, I don't have any experience with this. I haven't looked at different modes of like writing code. But anyway, we should check if this compiles and runs. Seems to compile and run, so that's good. Nothing breaks. Let's add just a simple test case for store. I'm gonna, let's say, let's just do a test for 80, 0x80. Let's store a value back at some address. 0x80, and then let's store it back at 0x maybe. It's the absolute, right? So it needs two. Uh, okay, we got our first error. Unconstruct null not valid. Uh, should attach a debugger and check what happened, but it's probably here because it said something about string, so my guess is it's something here. basic string m construct null not valid. Wait, why is it doing null? Oh, I think what happened is we put in. Okay, we should do this. If instruction dot name equals null, then name equals so this way if I have a wrong instruction it will tell me because that will be null. Okay, let's see what it says this time. It looks fine. But why was it? Oh, I think it needs 80 needs how many bytes? STA. 80 needs 3 bytes. Why was it complaining? Is my table wrong? I know one of my table has a mistake somewhere. What is 80 now? 128. Oh yeah, it is wrong. I think one of my I knew one of my instruction is badly encoded. Um, did it print this error message? Yeah, okay, we did get the instruction error message. Perfect. So actually, instead of putting a return, you know what I'm going to do? Assert false here. So that way we don't produce bad code if there's a bad instruction. And let's test this out. I think the 0x80 needs to be properly written. The table was wrong. Okay, perfect. Uh, this needs to be in hex. How do I make it go in hex? It's a byte if I cast it to unsigned. Should be. Otherwise, I'll use printf. Okay, opcode wanted. Okay, perfect. I have to make sure that it was 80. Yeah, 0x80 is the store opcode. And it's what? Absolute addressing mode, store, number of cycles, 4. Okay, this is 0. So 128. Yeah, this one. Hmm. How did I miss this? And then X indirect is 81, right? Yeah, X index is 81. Perfect. I, I I was looking at it the other day and I realized that there was one of the entry in the table was missing. I didn't remember which one. Turns out it was the store one. Invalid addressing mode 4. It's not. Oh, store doesn't have hash. Sorry, it's curious. Yeah, that's good. Store should not have indirect addressing mode. Uh, sorry, absolute addressing. And there we go. So it's just storing the value at the address we have provided. Doesn't set any flags or anything. So this should be good. Okay, great. So we have the store instruction. So see, that's what I was getting at. Like now that we have implemented all the addressing mode, at least the basic ones, adding more instructions now it's just a matter of like higher level description of those instructions, and then the code generator will take care of stitching together the addressing mode and everything. So let's go to the next one. Actually, let's go in order now. There are some jumps we need to do. Actually, you know what? Let's do a jump on 0 because there's an interesting thing I want to check. We need an INC for it, obviously, because let's see. Jump. Branch. I think it's branch on no zero, something like that. Yeah, branch on result not zero. That's the one I need. Um, there's also, yeah, these are interesting ones. So let's do this. Else if name equals to branch of result not zero, right? So BNZ, okay? No, BNE, not equals. Okay. So what does this do? Uh, this first of all, let's load its manual. So BNE has only one addressing mode, which is relative. What it does is it goes that much offset forward. So actually, let's look at relative addressing mode. This is one of the things we did not implement for loading because relative is only used for jumping. This mode is used with the branch and condition instruction. It is probably the mode you will use most often. A 1 byte value is added to the program counter, and the program counter continues execution from that address. This is for the normal one. The 1 byte number is treated as a signed number. That is, if the bit 7 is 1, the number given by the bits 0 to 6 is negative. If bit 7 is 0, the number is positive. This enables a branch displacement of up to 127 bytes in the either direction. So, an example. So if you have BEQ A7, this instruction will check the 0 status bit. If it is set, 39 decimals will be subtracted from the program counter and execution continues from that address. So let's see. We have A7, which is minus 39. This mode is related to the branch and condition. If it is probably a 1 byte value is added to the program counter and the program execution continues from that address. The 1 byte number is treated as a signed number. That is, if the bit 7 is 1, the number given by the bits 0 to 6 is negative. If bit 7 is 0, the number is positive. Okay, so we have to load 1 byte as a relative offset and interpret it as a signed byte, basically, like positive or negative. And then based on that, we have to change the program counter. So this is an interesting case because our program counter is currently a static variable. It's not a dynamic variable. So what does that mean? It means in our first stage, we have the value of the PC. Uh, that's good. That means we can do all the evaluation for the relative offsets and everything completely in our first stage. It won't generate any code for us. So let's see if we can do that correctly. We first need the byte stored at that location. So we're gonna say NES byte. It's not a D byte for now. Okay. Offset equals uh, instruction of 0. Oh, sorry, not 0, 1, because we not instruction of 0, we have instruction of 1. Great. The byte. And now we have to take the signedness of it. So I'm gonna say signed char uh, signed off equals offset. And hopefully, actually, no. What I should do is let's make a type called s byte, which is a signed byte. Right? We have the signed byte now, and I'm going to cast this as NES S byte first start. So that way I'm loading directly as signed value. I don't have to do any casts. Okay, so now I have a byte that's loaded as a signed value. And now I'm going to say PC plus equals to offset. That's all I'm doing. I want to skip the part where this PC equals to PC plus instruction size happens. Uh, so I'm going to put a continue. But here's the thing. This needs to happen only if the bit is set. So I'm going to say if um, context dot what is it, sign flag or zero flag or zero underscore flag. If the zero flag is set, then do this. Otherwise, do nothing. Otherwise, proceed normally. And in this case, I should just put a continue so that I don't do the stuff afterwards. Right? We just want to directly jump. We don't want to do this PC equals to PC plus instruction size. And this is it. This is the implementation of BNE. You realize we have a check on the dynamic variable, but inside that we're just updating the PC. We're not generating any code. There is no branch generated in the code. Let's see how does that work. I mean, I haven't done an instruction like that yet, but we will test it out. Okay. First of all, we need to clean this up. Invalid cast term and instruction. Oh, that's the wrong type. Uh, Main memory of PC. Okay. Okay. Let's just see if everything works fine. Great. Now I'm gonna actually comment this out. Let's test this other program. Huh? NES, NES byte program equals. Okay. And here's what I'm gonna write. First, I'm gonna put a load absolute. Uh, I'm just copying the stuff from before. At the end, there's going to be a 0xFF to stop the execution, so you don't run infinitely. And in the middle, I'm going to put a um, uh, jump on equal. So what was the thing for that? DNE. So this is D0, and then it takes 2 bytes. So I'm going to say 0x D0, and then I need to go back one step back. So how do you do that? Hold up. This is not 2's complement, is it? Come on. I don't think it's 2's complement. I think it's 1's complement. That's the problem. So we can't just use X and Y. I think we have to mask the higher bit and do a conditional check there. That's okay. It's all in the first stage. That's good. There we go. Yeah, the representation is exactly the same. So it's a 1's complement. Okay. Let's go back to having our original code then. Let's load the byte and then let's ask it for the sign. So this is not required, which means I can simply do main memory of PC plus one. All easy peasy. Okay. Now I'm gonna do if OFF and 0x, what's the highest bit? I can just add B. 1, 0, 0, 0, 0, 0, 0, 0. Yeah, whatever the binary representation. If the highest bit is set, then do PC minus equals um, OF F and 0B0111. I know what this is. X7F. Right? So yeah, else I should ideally do this, but doesn't matter because the highest bit is 0. That's what we just checked. Okay, I'll put this in a module eventually, but in a function. But yeah, what we're checking right now is if the highest bit is set, then subtract the offset. If it is not set, then add the offset, and that should give us what we want. And I was changing the driver. Okay, so 0D0, and now I just want to jump two instructions back. The PC is currently pointing at D0, and I go back to D9. Sorry, A9. So if I were to jump forward, it would have been just two, but I need to go back -2. So what I'm going to do is I'm going to see what that stands for. So 0B 1 0 0 0 0 0 0 0 or 2. So it's 130 in hex. That is 082. So 0x82. Okay, it's gonna give us a jump. Let's see what it produces in the generic code. This is like logically going back to the position, right? And here we go. We got something. We got a while one. We got a while one here. Uh, Surprisingly, there is a loop. We didn't expect it, but there's a loop. And then we have a load inside it, which takes the value 177 and sets it to the register accumulator. Now, okay, so here are things we can automatically optimize actually. Because it was using a constant value, we could have optimized this setting of the flags completely. Like this doesn't need to be done. But the thing is, the compiler will take care of this. It knows that we are setting a constant value. It's not gonna bother. And so here what we have: if not of reg flag z, which means if the flag is not set, then break out of this loop. Otherwise, go back to the execution, which is exactly what we wrote. We essentially like because BuildIt sort of sees the execution going back under this one specific condition. It says, hey, I'm not gonna like do this again and again. I'm just gonna make a loop out of this. So even without actually writing a loop, we got a loop in our generated code. That's because the program that we are interpreting has this specific loop under this condition. So this is actually very powerful. Now this is letting us create control flow that doesn't exist in the original program based on the control flow in our written program. And that's the one of the benefits of doing it this way. We could add like, okay, if I wrote another loop after this, which goes back, say this would need to go back 4 steps. So it would be like this. Let's see what that produces. Like I have a loop after a loop basically now. Uh, we still get a single loop. That's because we're checking the same condition and you're looping back to the same thing. It produces something else. So what I could do is I could put another instruction in the middle, suppose. And in this case, I'm going to go back 6 steps. Yeah, so this is slightly different. So that way it's not the same loop. And let's see what it produces. Uh, So this is our okay. So in this case, we got to continue. So it's saying that if the flag is set, the zero flag is set, then go back to the beginning. If the zero flag is not set, it continues and it breaks out only if the flag is not set. So it's logically correct. It's just not. Maybe if you want two loops, we could do uh, this uh, this way. And this inner loop, this is not required. This goes back 2 and this goes back 6. Okay, let's try what this gives us. This should give us a doubly nested loop. And here we go. We have a while one outside, which basically does the first load into the register, then checks the flags. Then the second, and inside this, it goes back, it doesn't have the going back code. Then we have the second loop, which runs till the flag is set. And then finally we have this one, which, yeah. So basically what we wrote is happening. So we have the first load, the second load, the first loop, and the second loop. Like, yeah, it gave us a doubly nested loop. So what Millet is basically trying to do is, if I was supposed to interpret this at runtime, and here is the sequence of instructions I saw, what is the control flow I could create out of it? That's what it ends up doing. There's no like This loop, we did not write this loop. This while one was not written. We just did a sequence of operations and updated the PC accordingly, and that got it to go back and forth and sort of like create these loops out of it. But we don't have to worry about this. We are not writing these programs. The end users, like the ROM has this code, so we should just interpret it as it is. That was our BNE instruction. We need to implement a few more instructions, so let's go through that. That's gonna be a bit. Uh, so let's see what the next instruction is. But yeah, if there's any question about how well it worked in this specific case, I can answer that. Okay, let's actually go in the order now. Um, or maybe we wanna do like some examples. Let's do a mem copy example. I have been actually meaning to do this for a while. Uh, let's write an example of a code where we copy the value from a location in memory to another uh, till a condition is met. So this is going to be writing some, not even assembly. This is writing byte code, bytes by hand, which is always fun. But let's see. 0xff always. Okay. So I'm basically writing a mem copy implementation in 6502. So which is basically doing for, or actually, um, while y is not equals to 0. Actually, I need a register for that. So while x, where x is a variable, is not equals to 0, do um, some location. So like say z of x, the x register here, x reg equals to um, y of y reg, right? These are actually, we can use the same pointer for this. Oh, sorry. You can use the same pointer, right? You can do y of x reg. Yeah, so I'm going to copy values over and then I'm going to do x reg plus plus, which means, yeah, x reg plus plus and x minus minus. This is the kind of program I'm going to implement and see what needs to be done for this. So let's assume that xreg and yreg are, we need to initialize them to 0. Mm, let's assume they're initialized to 0. It doesn't hurt. And then let's assume that x is initialized with the length of data that we want to load. So what do? We do a load from y and then we do a store at x. So let's assume our loads and stores are both happening inside the 0 page just for ease of doing it. And yeah, so we could write a backward xreg, yreg. We still need the increment and decrement instructions, which we haven't written yet. We should come back to this. Let's actually take a break for a second. Actually, maybe we're close to finishing, but let's take a break for a few minutes and then I'll come back and work on the rest of this. Just need to use the washroom and get some coffee for myself. I'll be back in like 2 minutes. Let's get coffee and use the washroom. All right, I'm back. Got myself some coffee. I don't know if I should be drinking coffee at around two, but it's okay. Yeah, so I want to write this function which sort of does a mem copy sort of operation. I need to see how DEC works first. Does it allow? Yeah, we have DEX and DEY. So let's implement DEX and DEY, and that way we can like implement this whole instruction. So else if name equals DEX. I don't think this has any addressing. It just increments and decrements X. Yeah, X minus 1 is stored in X and it sets the N and Z flags. Perfect. So again, because everything is in context dot xreg, so what do we call it here? Xreg equals context dot xreg minus 1. And this minus is going to be with wraparound just because we're using bytes as the data type. And that's it. Uh, I just need to do set n context dot xreg. Oops, and z. Okay. Yeah, you're setting it on the variable itself. And that should be dex. Let's complete the code. Um, let's test it out. So what is dex? Dex is CA. Hmm. Cannot convert d byte and unsigned char to a R value of NEST byte. Hmm. Yeah, you know what's happening. This requires a NES byte. An xreg is a T word, right? What is the width of the X and Y registers? That's actually a good question. I never checked that. Maybe the registers are small. Well, let's Google. Uh, 6502 register width. I think X and Y might be both um, a byte too. Mm, here we go. Registers. I think this website is down. There we go. Address mode instructions registers. Oh, X and Y are both 8-bit. Perfect. That's easy now. But that means I have to change a bunch of code that we wrote. Okay. Uh, PNES word. None of those were words, so okay. Emulator.cpp. This is fine. And then runtime also needs these to be byte. If it was not the case, then we would have to write a separate version for 2 byte set n and set z. But that's okay. Unfortunately, we don't need it. Sorry, fortunately, we don't need it. Oh no, no. I think this should work now. Okay. There we go. We have our regex equals to regex minus 1. Perfect. Again, let's see if this is optimized properly by the compiler, because this is something that I think it should. The flags should not be compared or anything like that. It should be able to do it directly, because x86 has instructions for this. Should probably make a way to test this quickly. There we go. So we have a move for, yeah, that's loading the regex from global memory, then moving it somewhere else and subtracting 1, testing, and then setting flags. Yeah, I think this is fine. This is how optimized it can get. What we're gonna do later is we're going to defer settings those flags for set it only if the next instruction needs it, like the instructions that comes afterwards needs it. That way we're not constantly setting it. But also once this becomes a local variable, like all these like flags and as flags become local variable, this will become much more easier to like optimize for the compiler. So we'll see how good the code gets later. But for now, I think DC is what we needed to write this memcopy. So now I'm going to write this loop. So let's see. We have let's give like basic addresses. So let's say Z the memory, or let's call it destination. You know what? It's easier. And let's make this xreg. So we are going to use xreg for everything. Yep, this is how we're going to write it. Easy. So destination of xreg equals to source of xreg minus minus. So let's say destination is the address 0x uh, 0x80, and source is, remember we are writing it backwards, so 0x, let's say 70. And these are two addresses that we're copying between. Uh, so here's what we're gonna write. We're going to first load the value from source. So that's going to be LDA. Oh God, I need to write the instructions by hand first and then maybe decode it. Let's do it. LDA 0x 80 comma x, right? And then I'm gonna do sta 0x for my sanity comma x. Uh, yeah, and then I need uh, decx, and then bne minus whatever the pne to the lda and stuff. Okay, this is what you want to write. So how do we do this? LDA with 0 page x indexed. Okay, 0 page x. 0 page only allows x, is it? Okay. 0 page x is B5. 0x B5, and then it's gonna be 0x70. And then we have to do a store. Again, 0 page x is 95, 0x95. So this gets 0x95, comma 0x80, right? And then we do DECX, which is what? Just wrote this. CA. and then we do a BNE. And the BNE was, I think this one. Yeah, 0xd0. We have to compute how many bytes. So dxd0, we have to go back. Oh wow, 0xd0. 1, 2, 3, 4, 5 bytes. So it's gonna be 0x85. Yeah, and then we need the 0x after to make sure that we input that program. Let's see what this produces. This is supposed to produce something like a man copy. Uh, but I'm curious to see what it produces. Okay, so we have a while one, and then we have a load at var 0 of regex plus 112. Great. And then we have reg accumulator equals to var 1. That's great. Then it sets a bunch of flags, and then it does loads the reg ACC into var 2 and stores it at 128 plus x. Great. And then it does regex equals to regex minus 1, checks the flag. If the flag is not set, then it breaks. Great. Uh, no, so it should be the other way. It should be branch on not zero, right? Yeah, it should go back on not zero. So let's see what the instruction for that is. BNE. Yeah, did we instructions branch on result not zero? How did we implement BNE? Oh, we did it wrong. It should be this, right? Not if it is not zero, then jump. Okay, yeah. You. Okay, and there we go. It has a not of not. Just fine. Compile and optimize. So what we get here is if the reg flag z is set, then go back, which is no, then break. Otherwise, continue. So this is good. This is what we wanted. Now let's see if we compile this. What do we get? This is a problem. My terminal gets stuck when I do Control R sometimes. I should not do Control R. Should fix this. Sorry about that. Let me. If anyone knows how to fix this on WSL, by the way, I would really, really appreciate this. Uh, it has been happening since for okay. Obj dump dash s scratch. There we go. So we got a bunch of instructions that do the copy. So we have loads, instruction sets, and subtraction, test, jump. Okay, this looks almost like what we want, but let's actually get rid of some of the unwanted code. Like this is not required, right? We're doing this because the how the implementation works. This is also not required. You only need the zero flag. This is the simplest version. I'm just manually changing the code. We'll eventually get to this when we do the optimizations. And let's see what this does for us. If we had produced the optimized code, what do we get? We still get a bunch of conditions. But okay, let's look at what we get. So this is, I need a linked version of this because these offsets are not filled in. 0 RIP EAX, NOPL, why is this a NOPL in the middle? So it loads the value from, no, this is the load and this is the store. These are just loading the value of the accumulator itself, of X and reg Z itself. So this is fine. And then, but yeah, but the point is we got a jump that goes back to here. So what's happening is because there's a lot of global loads and store, the backend compiler is not able to argue about what I should do to optimize this because it sees, okay, you're writing to a global variable and there's a bunch of other code there. I don't know if they overlap, so I'm not going to optimize it. But so to fix that, what we're going to do now is tell the compiler that, oh God, I close my whole session. Okay, so we're going to tell the compiler that, hey, look, your code is not, you're not accessing global variables. You can actually make local copies of them and we can send them back later. So inside our emulation, what you're going to do now is for all of the flags and variables that we have, we're going to create a copy and we're going to load them from the actual global ones. That way we get like, you'll see what that does. So DNES byte ACC, or I'm going to call it LACC equals to ACC, and DNS byte LXREG equals to XREG. These are just like reading from the global variable. NES byte LYREG equals to LYREG. DNES byte L carry flag equals to carry flag. Zero flag equals to zero flag. DNS byte. And then we'll use the local versions of the variables. That way, it's only going to make local changes to local variables. And that way, the compiler can optimize it. It knows that the loads and stores are not affecting any of the global variables. And we'll synchronize it back before exiting. So that way, we don't screw up our copies. DNS byte, decimal flag, overflow flag equals to flag. We're not going to copy the memory though. That's going to be expensive, so that's fine. And these are fine. And now what I'm going to do is I'm just going to add the local, I'm going to use the local version inside the context. This is part of the reason why I created that whole context struct that I can change later which ones we are actually working on. If you remember inside, those are just references to actual dynamic variables. So now I can change which variables am I actually working with, which comes in handy. No, 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 no. Let's see what this produces. Well, break flag was declared in the scope. Did you mean break flag? What was break after decimal? The reason I'm doing these loads is because the actual incoming value will be initialized inside the load. So that needs to happen. All right, let's try running this and see what we get this time. Oh, I never ran it. Okay, so this time again, it produced the same, almost the same code, but instead of like modifying the global variables directly, we are modifying the local variables now. So we made copies of all those variables. Also, why is var3 not initialized? Okay, I'll check what this is. So we have a bunch of variables initialized, and then we use those variable locally. So these updates to these local variables, the compiler knows for sure that it's not affecting any of the global variables, so it can optimize this better. I'm gonna check what the third initialization was after. Oh, here we go. Yeah. So this is gonna give us some optimization opportunities. Okay, let's compile this and see what we get. There we go. Much shorter code now. There isn't like any of those flag settings and stuff because it optimized it by itself. It knows that, look, I'm not doing any of these useful things. There's no more global load stores anymore. There's one global load at the beginning, which is to load the I think this is the array, the X register. It's loading that, and then it's using that constantly to do. I don't know what this instruction is though. Why is there a NOP in the middle? Maybe for alignment, but I'm not sure. Is this a jump target? Yeah, this is a jump target, right? So because this is a jump target, it's aligning this with a bunch of bytes. That's my guess. Uh, but yeah, so here we see there's an actual load from the X register. It's moving that uh, value to EDX, then doing a load on that value, doing the store on that value, subtracting one from AL, which is our value here, and then if it's not set, go back to zero. See, all the other stuff that we had got optimized this time, which is great. Uh, yeah. Unfortunately, the compiler couldn't optimize this into a memcopy. Like normally compilers, if you had this kind of code, they'll optimize it. The problem is those values, the base addresses, and they're all indexing into the same main memory. So it doesn't know anything about if those addresses overlap or not. Like it doesn't know if that X uh, addresses are far enough from each other that you can use memcopy. Uh, uh, but if we write a different function, suppose we wrote, instead of writing a memcopy, suppose we wrote a memset. So uh, let's try a memset implementation with this. It's also going backwards, which is hard for it to reason sometimes, but yeah. The compilers can catch a lot of things and convert them into like useful programs. But let's see. So let's say while xreg is not equals to 0, destination of xreg equals to say, let's do a byte, like say A, right? This is going to give us a memset implementation. So the load remains, no, there's no load anymore. There's a store at 80 at Y, but we need to put the value in. So I can put the value in once though. I don't need to set it again and again. So I'm gonna do 0x was the absolute load. A9. Okay. 0x A9, and I'm going to put some value. Like I don't know what's actually, I can use this. It's the good point of writing C. So, and then we have the store, then we have the decrement, and then we have a jump back 5 bytes again, and then we have the end. Okay, let's see what this does. Oh, wait, it shouldn't be 5. It should go back just 3 because we don't want to load again and again. Yeah. Let's see what it produces first. So we have there's a load at the beginning which has a bunch of checks after, but that's okay. Those do nothing. And then we have the actual store, then decrement, flag check, and break. Perfect. This is what we wanted. Let's compile this and see what we get. There we go. We got a bunch of optimized code. Again, this is the load from the registers from the global memory. Then we have a bunch of stores, subtract, and journey. I don't know why this was converting into a memset. It would be nice if it would do that. I think the problem is doesn't know if it goes out of the array bounds or something. Actually, no. Why is it not converting into a memset? Maybe because it's going backwards, not forwards. But my hope was like if it had actually maybe Clang might be able to do it. No, Clang actually did an even worse job. What the hell? Why did we had O3 for this, right? Oh, for some reason Clang did a bunch of nodes and stores with like comparisons and XORs. Oh, produce a bunch of copies. You see this? I need to take this to an expert. I need to understand what what the hell did Clang do? Let's look at the LLVM dump for this. Clang 03. This is a lot of complicated code. I do not understand what this is doing. Uh, I'm gonna run this by actually, not. Let's trim down some of the code first so that we don't have all the garbage. For example, we don't need we need all these things. We don't need this setting of the flag. Maybe this is causing confusion for it. We need these. We don't need the negation flag. We need the zero flag. Okay, this is the small make. It's still very complicated. I think it's expanding that into a mem copy of some sort, but not calling it mem copy. Okay, let's see this. Like it definitely made into a bunch of vector sets. So if you look at this, the 61 is the value that we were writing. It did a bunch of vector writes. So depending on what value of the actually that maybe there's a way to do this. If we can set x, we can do it. So like the value we are reading from, I'm going to initialize it. So I'm going to say I'm just manually going to do it. Reg underscore x equals to 128. Now it knows that I'm doing 128 bytes of copy. Let's see what it does. No, it's not set. There we go. Look, this is what I wanted. I wanted to show that if the compiler knows enough about your code, like if it sees all the actually, you know what? I'm gonna regenerate it this time and not remove any of those branches by hand. Let's just keep it and compile it with Clang and see what it produces. Um, yeah, here we go. And I'm just going to change this to add a size at the beginning. So it knows what size it's copying. Usually in your code, the assembly code that we're going to interpret is going to have some size somewhere. So that's good. Also, what the hell is that 97? Oh, that's the first load. Okay. So I'm going to just say edge underscore x equals to 128 bytes to copy. Right? Here we go. So it just produced a bunch of move UPS vector moves to do the store at the buffer. We did not write this code. We just wrote a simple interpreter that interpreted that mem set written in 6502 assembly, and we got the vectorized code out of it. This time I did not change anything. Like this time I kept the whole thing with all the checks and everything. But Clang being Clang, it automatically optimized everything. It knew that this is a bunch of like same value being saved again and again. So I'm going to optimize this into like a bunch of things. If I actually made this size larger, like if I did it like bigger, eventually it will start using memset. That's my guess. Oh, but this won't fit because let's do 256. Let's try 256 maybe. Doesn't like it. Uh, let's try 255. Yeah, it needs to be a value that it fits, right? Okay, great. And okay, this time it still produced like a bunch of vector moves and then like a sequence of stores after that. This is really cool. I mean, if the size was larger, it would have reason to call memset instead, but it saw that this is more efficient than making a function call, so it just put a bunch of stores. We did not write this code, it automatically optimized this. So this is the advantage of generating C over like generating assembly directly inside your JIT for the NES if we had done it that way. And that's part of the reason why I wanted to redo this project with BuildIt rather than doing it with like handwritten templates of stuff. Obviously, this is going to run much faster than if I had interpreted the original one, where like I had a bunch of loads and stores written in assembly. This is actually producing vector code, which is yeah, super optimized. Okay, so that's good. We have something working according to how we wanted. Apparently, only Clang is able to do it though. GCC craps out. for some reason. I don't know why. I was expecting GCC to also produce the optimized code. It got some things. It got some load stores, but it didn't get like the vector versions. It did like a repeat store. Yeah, it did a repeat store, which is fine. I guess that's optimized too. They both have different sort of cost models for these things, and they made different optimizations decisions. Clang decided to do vector. This decided to do stores. Yeah, uh, this is cool. Um, Now I'm gonna go back to adding more instructions. I think we have like 10 more minutes before I wrap up today's stream. I'll try to get it in a state where we can just keep on adding more instructions later, and we'll do that in the next stream. I won't do it offline. I'll so that everyone can be part of writing and debugging these instructions. Uh, yeah. So and I'll push this code so you guys can also play with this. And test it out on your side. Clone this repo. Make sure to build it inside the submodule before compiling the whole repo. Otherwise, you'll get like some linker errors. But yeah, let's go to the next instructions. Now this should be fast. Now you can just like quickly add instructions. ADC, add memory to accumulator with carry. Easy peasy. Uh, Got it. So it has immediate zero page X, absolute. It just loads a value and then adds it to carry. Sorry, adds it to accumulator and sets the carry. Okay, this shouldn't be too hard. So let's do this. Uh, it probably maintains some semblance of ordering here. Okay, so what do we need to do? We need to load the value using that our written data first. So DNES byte data equals load byte, right? We need this first. Okay, now we need to add this to the accumulator with the carry. Now the good thing is our carry is already in a byte, so it's easy to add. So I'm just gonna do dnes byte res equals. Actually, I can just do accumulator, right? Yeah. I can simply say context.accumulator equals to context.accumulator plus data plus context dot carry flag. Perfect. But I need to know if this is gonna overflow. So how do we do that? How do we know the carry bit of a result? I just have to check if it's more than 255. Is that right? Yeah. But that means I have to do the operation in a higher size. Yeah. So what I'm gonna do is I'm gonna use a word for this. DNES word. DNES word. Yeah, this will not work. Actually, no, this will work. So we cast the ACC to the higher width first, then we add it back, and this is gonna be just res. Okay. And now I need to do context.acc equals to res 0xff and context dot uh, carry flag equals res shift 8. Yeah, this should do it. So we take the higher bit if it is set. If there is any value set in there, then we set the carry flag. Yeah, this should do it, I think. Yeah, and then we also need to set Z. C is already set. N is already set. Sorry, N and Z need to set. Sorry. My bad. So set N and set Z, but not with data. We have to set it with. That's not used to see. We have to check what the difference between the carry flag and the A overflow flag is okay. The carry this holds the carry out of the most significant bit in the arithmetic operation. In subtraction operations, however, this flag is cleared, set to 0 if a borrow is required, set to 1 if no borrow is required. The carry flag is also used in shift and rotate logical operations. And what's the overflow flag? When an arithmetic operation results produces a result too large to be represented in a byte, V is set. Hmm. This holds the carryout of the most significant bit in the arithmetic operation. Isn't this the same for add? Uh, this holds the carryout of the most significant bit in the arithmetic operation. So when you're doing an arithmetic operation like a plus b, it holds the carryout of the most significant bit. Yeah, this is fine. I mean, if the most significant bit overflows, then we have, yeah, this should be fine. The subtraction case will take care. Uh, oh, also D, C, and they should probably also set carry maybe. I'll check what they said. DEX. Overflow flag. When an arithmetic operation produces a result too large to be represented in a byte, V is set. So yeah. Oh, it doesn't clear it otherwise, is it? Yeah, it is not unset. When an arithmetic operation produces a result too large to be represented in a byte, V is set. It doesn't unset it. Yeah, it doesn't clear it. So we just need to do if context dot carry flag, then context dot overflow flag equals to 1. Yeah, it doesn't get unset, so this is fine. And this should be ADC. To check if D, okay, yeah, we did the flags in D. Do we get carry also? No, just NNZ. Okay, great. So I think we did ADC correctly. We load the value, we add carry, memory, and accumulator, store it in accumulator, and set the carry. And N, Z, C, and V is set, which is what we have done here. Perfect. I think ADC is correct. Um, let's go to the next one. Next one is A and D. It does similar, but no other fancy flags, just N and Z. Okay, great. This is easy. See, now this is becoming much easier now that we have all the addressing modes written. We load the byte, and then we simply do context dot acc equals res and not res context dot acc and data, and then we can do set n on context. There we go. This is good. What time is it? We have 4 more minutes. Okay. I'm gonna do ASL, which is, oh, this has some carry shift, but so we'll take care of this. ASL shift left 1 bit. I think this is fine. This is exactly like add, just uh, I should have used a switch case for this, and I should have used enums, but that's okay. Keep writing an extra bracket. Okay, so I load. There's no data for this. This is, yeah, this is all happening in this. So I can do context dot. I need to move it to a, yeah, I need to load it in the wider word first. So DNES word res equals context dot ACC, and then res equals res shift 1, and then context dot ACC equals res or 0xff, context dot carry flag equals, yeah, so if there is a bit being shifted, we set it. What else does it require? It also requires the Z and N. So this gets it here. Yeah, this is part of the reason why I didn't want to like generically handle all the flags. I wanted to like write code for it because they deal with these flags in subtly different ways. It's not always the same. I guess I could have done N and Z in a very generic way, saying like mention it as a property of the instruction itself, like what flag it sets, and the interpreter can just like, okay, if this instruction sets N and Z, then set N and Z. But then it also depends on what value you're working on. Sometimes it's on like the ACC, sometimes it's on the data. I think most of the time it's ACC, but it's good to be explicit. I think it doesn't hurt. Okay, I think ASL looks fine to me. Let's go to BCC, branch on carry clear. This is very similar to um, our previous instruction. So I think this needs to be mod like sent into a module. Yeah, this needs to be uh, made into a function. So let's do this. We just need a static uh, NES S byte. No. We just need an integer. We can just get a positive or negative integer out of it. That should be fine. Uh, get relative offset. And what should this take? It should take the context, t context, and what does it need? Needs the main memory and the PC. I'll just take the byte then. NESD byte. Means I'm gonna move this inside. No. So if B. Wait, is this even? No, this is NES byte. It doesn't have to be D byte. Okay, if D and should be like yeah 80. If T and 0x80 return negative of D and 0x7F, else return D and 0x7F. Okay, let's go get relative offset. So now I can do PC plus equals get relative, is it get relative offset? Yep, in memory of PC plus 1. Okay, then this doesn't need to be there. This is it. I'm gonna copy this and is it branch on BCC, branch on carry clear, branch on C equals to 0. So we can just check. So uh, if the carry flag is clear, then we do this, else we do nothing. Perfect. Okay, so we are at 2 now, which means I should wrap this up. I'm just gonna make sure that this compiles, and then I'm gonna push all the changes into the repository, add it to the resource doc today, and also some of the materials that we used to learn this into the resource doc. Actually, it should be in the repo, so I'll link it there. And let's just see if this compiles. Yeah, this produces some of the code. I want this. This should be correct. Uh, niche commit with emulating The MOS 6502 microprocessor. Okay, so I have committed the code. I will push this, add it to the repo and everything. And I think I'll wrap up today for now. If you have any questions, if you have any thoughts, I'm always curious to hear about it. Next time, we will continue with first finishing all the instructions, which hopefully from now on should be pretty easy because we have all the basic infrastructure done. Then we will spend some time mapping the ROMs that we have. So we have like the Mario ROM and Donkey Kong ROM, how to load them, how to find where the instructions are, how to allocate memory for the data and stuff like that. There's a very nice way of how this is laid out in memory. There's like some duplication in the memory, and like one address range is mapped to multiple sorry, the same piece of actual physical memory is mapped to like multiple ranges of addresses. It's pretty interesting. We'll go through that, we'll implement that. And at that point, we will have like, we should be able to load a ROM and run it entirely. But the problem is then that's when we like start needing the PPU, which is the picture processing unit, where we'll have to then make sure that we are simulating the cycles correctly, go and draw the, at least in memory, not showing it on the screen, but at least in memory, draw the pixels and then give the feedback back to the processor so the whole game can run. And at the very end, we'll add like a controller so we can play the game, we can read those special address ranges and so on. That all comes as part of the, but what we're doing currently is emulating the 6502 microprocessor, which is different from the NES system. It's like the NES uses 6502. There's a lot more to NES than just 6502. So we'll spend some time implementing that too. And again, we'll be using BuildIt for doing the PPU stuff too, which would be a nice change from what I had done before. And yeah, that's about it for now. I'll wrap the stream here today. I'll see you, hopefully, folks, next week, maybe. Let's see. I'm not sure about my schedule. I have a paper deadline coming up, but I'll try to be regular. I'll try to finish this soon, and let's see if we are actually able to play some games. All right. Thanks, and I'll see you folks next week.